Okay, hello everybody. People are still joining, so greetings from Seattle. And today I'm going to talk about bias correction and interference bias in ranking experiments. This is a joint work with Anya Lambrecht from LBS and my colleague Hema Yoganarasimhanadula. Okay, let's get started. So ranking algorithms are at the core of many digital markets these days. If you go to Airbnb, Amazon, Expedia, Instacart, what you do is that you'll submit a query, then you're shown a rank ordered list of items. They'll choose among those, lists, and these ranking algorithms can affect, the user engagement quite a bit and end up having a big impact on platform revenues. Now, the platform's goal is to pick the best ranking algorithm among a number of algorithms that are at its disposal, and then deploy it on the platform, meaning all users are going to be assigned that ranking algorithm. The platform wants to measure the performance of the ranking algorithm when all users are assigned to it, which we call the total average treatment effect. So let's see how this is achieved. Typically, in order to identify the optimal ranking algorithm, the standard practice is you run an A/B test and you estimate Tate for each algorithm based on an outcome of interest. That could be CTR, that could be booking rate, and then you pick a winner. The caveat is that the performance of an algorithm is observed under the A/B test, which is when a random subset of users are assigned to it, not when it is fully deployed, not Tate. Now, under the hood, there's this assumption, the Sutwa assumption that we have, which is outcomes under one algorithm are not influenced by other algorithms or treatment cells. Okay. Now, are A/B tests of these ranking algorithms indeed valid? Let me give you a very simple example. Let's consider a platform that has two algorithms at its disposal, algorithm 1 and algorithm 2. Algorithm 1 is ranking hotel A on the top, followed by hotel B and C. Algorithm 2 has the exact reverse ranking. C is on top, followed by B and A. Okay. Now, let's, for simplicity, assume there are only two users on this platform. And let's say user preferences are hotel independent, only depend on the ranks. So a user will click on a hotel of rank 1, the top position of probability 1, position 2 will probability half, position 3 with probability 0.25, a quarter. Now, conditional on clicking, notice that I have another layer of complexity here. Every hotel has two rooms, the L room and the H room. Think of it as the low price room and the high price room. Now, if the user clicks on a hotel and the low price room is available, he will book it with probability 1. If not, they will book it with probability half. Okay, so preference for positions, and then conditional on clicking on some position, there is this preference for low versus high price room. Now, let's see what would have happened if all users were assigned to algorithm 1 versus if we were doing an A/B test and we're trying to measure the effect of algorithm 1 versus algorithm 2. Okay. If all users were assigned to algorithm 1, let's just focus on demand for hotel A under algorithm 1, which is the demand generated for hotel A from algorithm 1, which is now basically demand for all users from algorithm 1, because now it's fully scaled. Now, let's say there are two users. The first user arrives, and then with probability 1, they click on the first position. Room L is available. They book it. So that's the one you see here. And then second user arrives. Room low price of algorithm of hotel A is gone. They click on hotel A. Room H is available. They book it at probability half. So the demand per user for hotel A under algorithm 1 is 3/4. Okay. Now let's see what would have happened if you have done an A/B test. So if you had ran an A/B test, there are two scenarios. First, you would assign the users randomly either to algorithm 1 or algorithm 2. So the darker shade here, which is highlighted, these are algorithm 1, and then the blurred one is algorithm 2. So let's say user 1 is assigned to algorithm 1 with probability half. Then what happens is that they will buy the low price room with probability 1. and that's done. Okay, so there's a single demand for that algorithm, that for that hotel under algorithm A. Okay, now let's say we're in scenario 2. If you're in scenario 2, the first user is assigned to algorithm 2. Now in algorithm 2, the rank of hotel A is rank 3. Okay, now the user ends up purchasing the low price room of that hotel with probability 1/4. Now when user 2 arrives and it's assigned to algorithm 1, the low price room could be gone with some probability. Okay, now if you do the calculation, you will see that the average demand per user for hotel A under algorithm 1 is now different from what we had before, which is 3/4. Now it's 15/16. So if you repeat similar calculations, you will see that demand generated for hotel A is actually overestimated. Demand generated for hotel B is correctly estimated. Demand generated for hotel C is underestimated. And the overall demand is actually overestimated, okay, under the A/B test. So what happened here? By the way, if you have questions, feel free to use the chat. My co-author is here, Hema is here. She will try to address those. If that's not addressed, just feel free to interrupt me, okay? Okay, so what happened here? If you look here, hotel A is being demoted by algorithm 2, okay? So when it's being demoted, it means that the equilibrium prices when you run an A/B test end up being lower than what it would have been if algorithm 1 was fully scaled. Remember, algorithm 1 is putting hotel A on top, so it's more likely that it runs out of the low price route. Okay, so now the equilibrium prices are going to be different under the A/B test versus when it's fully deployed. So that's the source of discrepancy. Now for hotel B, the rankings are consistent. Algorithm 1 and algorithm 2 are putting hotel B in the same rank. Okay, that's where you see actually the Tate measure, the total average treatment effect measured under the A/B test, ends up being consistent with that measure when it's fully deployed. Okay. Now for hotel C, exact opposite happens. For hotel C, the competing algorithm, algorithm 2, is promoting it. So the equilibrium prices under the A/B test end up being higher than what it would have been if algorithm 1 was fully deployed. Okay, so that's why you actually have the Tate for hotel C being underestimated. Okay, so now you're probably thinking that there are a million other reasons where interference bias can happen. I just gave you one reason, which is in this case, it was just equilibrium prices. It could happen because of supply side constraints, strategic response by sellers, feedback loops, which is basically means the ranking itself depends on some aggregate outcome and could change as the mix of algorithms change. Now, naive Tate estimates based on A/B tests can be biased. I just illustrated with one example. Now, the problem is that you really want to simulate the counterfactual market equilibrium when the test algorithm is deployed at 100%, meaning all users are assigned to it. But you see this imperfect sort of experiments under these A/B tests where a subset are assigned to it. So what can be done? Any questions so far? Is the example clear? Okay.
Ali, actually, I have a question which I typed. If you don't mind, I can ask.
Yes.
This is Kishore. What do you mean by equilibrium prices in the example? I mean, when are they being set?
Okay, so let's think about it. If in this example, you run an A/B test, okay, what's going to happen is that the hotel is going to see some overall demand, okay, that is generated from users, okay? So under the A/B test, the demand that is going to see is going to be lower than when it sees demand when algorithm 1 is fully deployed, okay? Because algorithm 2 is demoting hotel A, okay? That probably lowers the overall demand that is generated for hotel A. What does it mean? That the equilibrium price under the A/B test is going to be lower than what it would have been if algorithm 1 was assigned to all users rather than say half of the users. Okay?
So basically what I'm trying to clarify is that the hotel is changing price inside, like in a short-term basis?
It doesn't even need to change the price. It's
Okay.
just demand shifts, right? And you run out of the low price rooms. In this case, there's a low price room, the high price room, the low price rooms run out, and then the price of rooms that are left are going to be higher. Okay. So there doesn't even need to be a strategic response. It's just, you know,
So that's why I was wanting to clarify the use of the word equilibrium. And
okay, great. So I see where you're coming from, but all I'm saying is that there doesn't need to be even a strategic response. Just by the mere fact that you have supply side constraint, this can be generated.
Okay, thanks.
Okay. And there are many, many other reasons that can generate this. It can be that the ranking itself depends on some overall outcome, and that ends up being shifted as you change the mix of algorithms.
Okay, thank you.
Great. Okay, so we're not the first to sort of document this. There is this paper by Blake and Coy. They actually documented for auctions ran in eBay. Their interference bias is large there. There is this paper by Fratkin. He shows by simulation in the case of Airbnb that the bias could be as large as 100%. Okay, now how do we address this problem? Typically, it's about running the experiment differently. So the solutions that are currently being proposed in the literature is that you have to run your experiment in another way. A big part of literature is basically saying you have to do cluster randomization, meaning that you have to do, say, your randomization at city level, at market level. That reduces the number of observations you have, will lower your power. The other stream of literature is that you have to do double randomization. These types of sort of techniques don't apply to rankings because it's about giving a sticker to a subset of sellers. These don't generalize to rankings. Now, the above solutions also have this caveat, which is basically all the historical data now is useless. Okay, so you have to change your experimentation platform. The idea is that can we somehow leverage the existing A/B tests and try to correct that bias, okay, without changing experimentation? Okay, now here's the agenda I have today. I'm going to talk a little bit about, you know, simple theories behind this. So how can we establish a framework here? Then we're going to talk about a novel solution, which is based on market equilibrium concepts. Then we're going to use empirical data from a travel agency, build a customized machine learning algorithm to predict the true state based on the A/B test that the platform has already ran. And then we're going to do counterfactual analysis to recover the state and quantify the bias. Okay, so let's get started. First, by the way, this was a keynote presentation. Somehow my iPad glitched, so this would appear in order, but now it's a mess. So 5 minutes before, I just uploaded the PDF. Okay, so let me parse this. Don't look at anything for now. This is the measured state. Inside the sum, I don't know whether you see my cursor or not. Inside the sum, I want you to focus. This is the demand generated for hotel J under algorithm A. So think about hotel A. How much demand is generated for hotel A through the traffic that goes through algorithm A? Okay. Now this depends on hotel features, things like location of the hotel, properties of the hotel, the rank that is being assigned to hotel J by algorithm A, the focal algorithm. As it pushes the rank higher, a better rank, probably the demand will go up, right? It will see more demand through algorithm A. But there's also another point. It also depends on the mix of algorithms and the rank they assign to this hotel. Because if the mix of algorithms is promoting or demoting the hotel, like the example that we had, those can affect equilibrium outcomes. Those can affect prices. Those can affect what kind of rooms are available. Now, when you sum this up, demand across the hotels, this is the total demand that the platform sees. Okay, that's what I call measured state. Okay, so that's the measured state under an A/B test. Note that the second term here, there's this PJM, depends on the mix of algorithms that are being tested. Am I interested in this? No. I want to see the true state, which is when this algorithm is fully scaled. So the mix of algorithms is exactly the same as algorithm A. So there's no inconsistency between the rankings of a hotel J and its ranking by the mix of algorithms. Now I'm making a couple of strong assumptions here. I'm assuming that demand for this hotel only depends on its own properties, only depends on its own rank, stuff like that. Also note that we should not include things that are equilibrium outcomes. So prices could very well change. I'm going to predict the counterfactual. And the counterfactual, the idea is that I'm going to look at this discrepancy between the rank of this item under a focal algorithm and how this item is ranked by the mix of algorithms. When discrepancy is low, you're close to quote unquote equilibria for that item. When it's far away, those observations are not reliable. Okay. Now, basically, the idea is that we are going to salvage imperfect A/B tests to detect where the interference is more or less pronounced. Now, the type of variation or metric that is going to be useful here is to use variation in discrepancy between an item's ranking within a focal algorithm and its ranking in the overall cohort. And cohort by cohort, I mean in an A/B test. So algorithm 1 is being tested against 2 in one cohort, in another cohort, maybe it's being tested against 3. Okay, so the type of variation across these experiments is going to help me, and I will make it more clear in a little bit. The intuition is that items with low discrepancy, they suffer less from this interference bias. Okay, so if there's low discrepancy between the focal algorithms ranking and the rankings provided by the mix of algorithms, those observations are going to be quite useful in identifying the true effect when the algorithm is fully scaled up. Now, the solution we have is that if you have data across a series of experiments, so panel data across experiments, we can pool low discrepancy observations to then learn tape. Okay. Okay. I won't bore you with Greek letters, but we are going to leverage 2 types of variation. There's the panel variation, which is if for each hotel, there exists a cohort where hotel J's rank within that cohort under the algorithm A is similar to its cohort ranking. Okay, then that's going to be very, very useful, because this means that if I scale up algorithm A, things don't change for this hotel much. Okay, now it could be that you can't find that those observations. Instead, if there exists a hotel J, which is similar, J prime, which is similar to that hotel J from the perspective of the algorithm A, and then J prime has low discrepancy in one of the cohorts. Okay, so J prime is in a good position. Then those observations are going to be informative in how hotel J would do if it was fully scaled. So these are these 2 types of variation that we are going to use. Now, if this was unclear, this figure, I'm trying to clarify the panel variation of this figure. So the idea is that, say you have 3 cohorts, and then algorithm 1 is being tested in all of these cohorts. So algorithm 1 is the left algorithm here, see here. Okay, now it is being tested against different algorithms, algorithm 2, 3, and 4, and they rank the items differently. If you look here, hotel B is in a quote unquote good position here, low discrepancy, because its rank is consistent between the 2 algorithms. Then hotel A has low discrepancy in cohort 2, hotel C has low discrepancy in cohort 3. If you pull these observations, it could be informative in informing what would have happened if all users were assigned to algorithm. Okay. Any questions so far? I don't see the chat, but okay. Okay. So here are good properties of the algorithm that we're going to propose. It's agnostic to the source of the interference bias. As Kinshuk also tried to elaborate here, there are many different sources where interference bias can happen, right? It could be simply because of supply side constraints. It could be that ranks itself is endogenous. If the rank of an algorithm has some feedback loop, meaning say the overall impressions go to the ranking. So the ranking itself is the function of mix of rankings. Or if equilibrium outcomes such as prices shift by mix of algorithms, then we could have this interference issue. Now, we do not need to know specifics about any of these ranking algorithms. We just need to know what kind of ranking distributions do they generate as a mix. So their mix is going to generate a distribution of ranks for a given item, hotel. We just need to know that. Okay. Now, the big plus is that the platform does not need to change their experimentation. Okay. So the experimentation method would not change, then they can also use the historical data. Okay, so that would be the big plus here. Okay, so let me talk a little bit about the data that we are going to use to establish this. Data comes from a travel agency. It's a large hotel booking website, and it's for 6 months. Person arrives, they put a query in, they get ranked results for hotels, then they click booking and so forth. They have about 43 million queries, 20 million clicks, and more than 900K bookings, and 54K hotels are on this platform. Okay, each query that a user submits receives about 0.47 clicks and 0.02 bookings. Okay, the platform is monetized by getting commissions on bookings. Now, our goal is to recover the true TATE, total average treatment effect, of one of the algorithms that are being tested. Okay, this is their core ranking algorithm, which is called Genesis. The platform ran 16 experiments, and Genesis participated in all of these experiments, meaning that a random subset of users were always assigned to Genesis. Okay. Now, it was tested against a variety of other ranking algorithms, was never scaled up to 100%. So I actually never observed TATE for Genesis. And we only see a series of contaminated measures of TATE under these different A/B tests. Okay. Now, let me parse what you're seeing here. On the top figure, you see the portion of traffic allocated to Genesis, and that varies across cohorts. So that could go all the way from 90% to less than 50%. In the last cohort, 16 and 15, here you get 80% of traffic is assigned to Genesis. Here, 60% is assigned to Genesis. Okay. Now, on the bottom, the top bottom panel, you're looking at the CTR, click-through rate. Now, what's interesting is that as cohorts change, you see this discontinuous shifts in CTR. It's the same algorithm. All of a sudden, the CTR keeps changing. Now, I want to highlight the last two cohorts. You see that it is scaled up from 60 to 80%, and the CTR all of a sudden drops. Okay. Now, I'm going to show you some reduced form evidence to argue that this is because of interference bias. Then I'm going to tell you how this model works and how did we build a machine learning model to be able to predict TATE from this observational data. In the reduced form evidence, I'm going to look at the last two cohorts. Last two cohorts are interesting for a number of reasons. A, there are two other algorithms that were concurrently tested in both cohorts. So there's algorithm 1 and 2, they participated in both A/B tests. Now, when you look at this and you look at CTR, the CTR changes discontinuously for Genesis, and the CTR of algorithm 1 and 2 are not affected. So when we saw these discontinuities at first, we thought, yo, maybe something at the platform changed. Maybe it was demand side issues. But this rules that out. And you can formally establish this with a different. You can do a difference in differences, and you will see that if you look at click-through rate or booking rate, it's changing differentially for Genesis relative to the two other algorithms. So algorithms are the same. All of a sudden, one of the algorithms is affected and its performance starts dropping. So what's going on? Okay, so let's see if we can sort of show that interference is the culprit. If interference is the culprit, then it must be the case that in one of these two cohorts, there exist some hotels that had high discrepancy, like remember that hotel A, right? And there are some hotels that in both cohorts, they had low discrepancy. 4 hotels that had low discrepancy across both cohorts, there can't be a drop. At least there can't be a drop because of interference bias, because they were both close to, quote unquote, their equilibrium position, right? They were in a good position. Rankings were consistent for those hotels. So the idea is that I'm going to create a measure for ranking discrepancy to see whether I can show in data that this discontinuous drop can be attributed to this mismeasurement because of high discrepancy. So let's first create a ranking discrepancy measure. Okay. By the way, in the full algorithm, we have more measures. There are more metrics that go in. This is just the simplest one that you can use here. You basically have two distributions. Given a hotel, there is a distribution of ranks that is assigned by algorithm A, and there is a distribution of ranks for this hotel that is assigned by the mix of algorithms that are being tested in this cohort. By the way, this is always distributions because the ranks are not completely stable, right? Something may run out, the query changes, the rank changes a little bit. So it's always, there's a little bit of uncertainty for even if it's the same algorithm, okay? So basically, I want a distance between two distributions, okay? Now, I'm going to take the simplest way to do that. I take the expected ranking under Genesis, and divide it by the expected ranking of that same hotel under the mix of algorithms, and take the log, okay? So this tells me how far off is the ranking of Genesis from the average ranking in that cohort. Now, if this is 0, it means that the ranks are consistent, like Hotel B, right? Hotel B, where ranks were consistent, 0. Now, if it's, for instance, 0.2, it means that on average, the algorithm A, the rank of Hotel J under algorithm A is about 22% higher than its average rank in the cohort. So cohort is generally promoting it, A is demoting. Okay. Now, I want to look at two different cohorts, cohort 15 and 16, the last two cohorts. I take the max of this discrepancy, create this overall discrepancy measure across these two cohorts. If this is low, it means that the hotel had low discrepancy in both cohorts. So if you look at algorithm Genesis, their ranking of Genesis and cohort rankings were consistent, sort of, in both cohorts. So there couldn't be a discontinuous drop in those hotels. So what I'm going to do is that I'm going to do a median split on this parameter, put it on low overall discrepancy, high overall discrepancy, and see how CTR changes for hotels that had high overall discrepancy and hotels that had low overall discrepancy. The idea is that hotels that, if a hotel has low overall discrepancy, then the measurements are less likely to suffer from interference points. This is exactly what we see, okay? So we actually do this median split. You see that the drop by high overall discrepancy hotels is much more pronounced than those that have low overall discrepancy. Now, let's see whether we can use this type of variation to build a model to then predict what would have happened if the algorithm was fully scaled. How would the demand change overall? Okay, so again, I apologize. These were keynote talks. Now, again, some big thing is gonna show up. I will go through it one by one. So basically what you want to see, or what you want to measure, is the overall number of clicks generated when an algorithm is working, okay? So clicks that are generated after traffic is redirected to an algorithm fully, okay? Now, the way I'm going to model that, I'm going to take the queries that are assigned to a hotel, to an algorithm, okay? This I take as exogenous. Here is the probability of a hotel being shown on that query response. And then it's a function of hotel characteristics, seasonality features, which will explain what goes in here, and then a bunch of discrepancy features, okay? Now, disregard this equal to 0 for a sec. In the data, you observe a hotel. Sometimes it's under high discrepancy, so the rankings are not consistent. Sometimes it's under low discrepancy, okay? So you want to learn how the impressions change when you have a query, conditional query. And then you do the same thing, clicks conditional on impressions. So for each hotel at each day, you want to see how many impressions does it receive and how many clicks does it receive after getting those impressions, okay? And now, one of the important features here is this discrepancy. Now, you are interested in evaluating what would happen if discrepancy is 0, right? But that is when the ranks are completely consistent, right? So I'm going to use this type of variation, okay? Now, I want to emphasize again, features that are equilibrium outcomes, like prices, rooms available are not fed into this here because those change as discrepancy changes, right? So this model should implicitly learn those things. Okay. Now, the model number of impressions as a binomial random variable and the log likelihood of receiving k impressions if q queries are run is modeled like this. Now, what we do is that the probability, this probability P naught, is modeled as a neural network, so as a flexible function form, which is a function of hotel characteristics, seasonality features, and discrepancy. Now, the idea is that I want to evaluate it at points where discrepancy is low. Okay. Now, we have a similar model for clicks as well, conditional on impressions. So basically, hotel features go in, seasonality features go in, and discrepancy features go in. Then you have a probability that is modeled as a neural net. Then they have the binomial loss function, which I just showed you. Okay. Now, what are the hotel features? Hotel features are a set of observable features alongside two representation vectors, which are based on GLOVE, if you have heard of GLOVE in natural language processing. So you have word to vec. This is like hotel to vec. And the way it does is that it basically assigns a representation vector for each hotel based on the co-occurrence of hotels in results and how they are co-clicked. So tries to figure out user preferences and if the hotels are similar to each other in the eye of Genesis. Okay, remember about that type of sort of variation we talked about? Even if the hotel is not close to its equilibrium position ever, if there is another hotel that is similar to this hotel and it's close to this to its equilibrium position, those observations are going to be useful. There's also seasonality features. I won't put day dummies because I want to predict out of sample. Okay, I want to predict out in the future, so I can't put day dummies. Instead, I create a representation vector for each day based on the top 5,000 destinations that are searched every day. Okay, so those are again transformed to a representation vector for each day. And there's also the discrepancy metrics. Apart from the metric that I showed you, which was the log ratio of expectations, I have more discrepancy features, which is the log ratios corresponding to deciles of Genesis and cohort. So this captures a better sort of distance between two distributions.
Sorry, can I ask you a quick question?
Yep.
So you mentioned earlier, like 2 slides ago, because of that discrepancy, you don't include the room prices because that information is included as part of the discrepancy variation. Because initially you talked about supply side constraint, like there's a supply constraint, there's not enough rooms, and the hotels change their price based on the occupancy. And then you kind of switch to discrepancy in ranking. So I was wondering where that room price is, how that's incorporated in your model.
So imagine if I had used prices. Okay, prices themselves, as I showed in the example, are a function of how consistent the rankings of this algorithm are with the cohort rankings, right? In that hotel ABC, if you are in the A/B test, the prices could be different. Okay. Now, if you feed it in, you want to evaluate what would have happened in the counterfactual. This means that you have to feed in counterfactual prices if you are to use that, but you don't know the counterfactual prices. Okay. So you are left with 2 options. Either you need a separate model to learn counterfactual prices at the same time. Okay. Or you need to say, I will learn a model. I won't include counterfactual prices, but this model will take whatever it has as exogenous stuff to predict the overall demand, which implicitly it has to learn, whether it's prices, room availability, because there's tons of different reasons where interference can happen. It has to learn the overall impact in a single model. Okay, so that's the problem. You don't want to include endogenous variables in the prediction. That would create problems. Okay. Now, what kind of variation you're using? For most hotels, there exists a cohort. Remember, there were 16 cohorts. There exists at least one cohort where the discrepancy between Genesis rankings and the cohort rankings are low. This is what you see in this picture. I'm calculating the minimum discrepancy across cohorts for each hotel. You see how it's centered around 0? It means there exists a cohort for each hotel where discrepancy is low. So I have opportunities to see you close to your sort of good position, equilibrium point. This is the average of that thing, that same thing, discrepancy for each hotel. You see, it actually deviates from 0. So on average, hotels are not in a good position. There's no consistency. Okay, but if you take the best place for each hotel, then you see there's this spike at 0. Same idea for hotels that are similar to me. If I use KNN in the hotel feature space, if I just look at the best position that me or the closest hotel are similar to me have versus the top 10 hotels that are similar to me, you see more opportunities, right? So if you are willing to look at hotels that are very similar to me, to a hotel J, you always have opportunities where discrepancy falls. Okay, so there is useful variation in the data to identify it. Okay, now for the counterfactual analysis, I'm going to train a machine learning model, learn impressions, learn clicks. What I'm going to do is that I'm going to take the first 15 cohorts as training and validation. I'll never show cohort 16, last cohort, to my model in any way. And then I will evaluate counterfactual performance by setting discrepancy features to 0. So I'm going to learn, see what happens, and hopefully it learns the outcomes in the neighborhood of 0, discrepancy equals 0, and then you're going to evaluate the outcome of your model at 0. Okay. Now, here's the predictions of the CTR, the blue, the circle blue or whatever, if it's green. This circles are the predictions of our model of the CTR. Okay. Now, what is really interesting is that if you look at the previous figure, which I will show you in a second, on cohort 8, Genesis was deployed to 90% of the population. So in sample, at least, you see the difference between the blue and the red are very low. So at least in sample, low discrepancy observations, the prediction of the algorithm is that Tate was measured fairly well. Why? Because a large portion of population was assigned to Genesis in that cohort. Now, what's also interesting is that in cohort 16, when you move from 15 to 16, Genesis was a scaled up. Okay, it was a scale up. Probably when you scale up, you are closer to Tate. And the algorithm has already figured out that the performance here was biased. And it's closer to what it would have been in cohort 16. Okay. Now, this is exactly what we had before. See, you go from 60% to 80%, performance drops, and the algorithm has managed to figure that out. Okay. Now, let's actually try to establish how large the bias could be. So if you compare the last 2 cohorts in terms of CTR, remember the last cohort is held out, so it was never shown to the algorithm. The extension of interference bias actually varies quite a bit when the traffic assigned to Genesis changes. So when you go from 60% to 80%, the bias goes down quite a bit. Okay, but the bias was fairly large when you were looking at CTR. We did the same thing for bookings as well. So we added a third model trying to predict bookings. And you see that, relative bias was fairly high. So you were far away from Tate, or at least the corrected Tate, when you were assigning only 60% of users to Genesis, and then it went down. Okay. So basically, the naive estimates of Tate on A/B tests can be significantly biased. Using our approach can help with mitigating some of that bias. Okay. Now, what did we achieve today? I showed you that A/B tests of ranking algorithms are biased. We tried to develop a novel solution that is basically agnostic to the source of interference. And there was a discussion right now why those endogenous variables are not included. And it can be used with existing data from previous experiments. So historical data can be salvaged. Now, I showed you some evidence from a travel agency platform that the performance of their focal algorithm changed discontinuously as the mix of algorithms that was tested with it changed. And we tried to quantify the relative bias. Okay, so bottom line is that you don't want to use A/B tests to evaluate how ranking algorithms do, or at least the results could be pretty biased. And this Tate sort of prediction algorithm can be used to correct that bias. I think I'm right on time.
You have 5 minutes. If you want.
Okay, we can have questions. I thought it's 40 minutes. So, any questions? I see that Amin has, does it matter if all or some of the algorithms in the cohort respond to supply changes in real time? So by algorithms, you mean the ranking algorithm. So the ranks could change. You're right. The rank could change as a mix of algorithms. So if you, this can't, like, there are some regularity assumptions for this to work. So in order for this to work, you need a uniqueness assumption, uniqueness of equilibrium. So you need to have, if you read the paper, you will see that we have this uniqueness assumption, which means that if discrepancy is fairly low, it corresponds to a unique equilibrium, which is you need a contraction map. So there is some assumption under the hood for that as well. So you basically need to have one set of rankings when discrepancy is 0. And prices are endowed. This is HEMA. Okay. So one way that this can happen is that a very simple way is that there are platforms that they just feed in the number of impressions that are sent or the number of clicks that are made on a hotel overall. If they go into your ranking algorithm, then it depends on the mix now, right? So if some algorithm starts promoting some hotel, the click-through rate goes up. If that feature is fed to the ranking algorithm, then ranks become an endogenous variable themselves. So ranks become a function of the mix of algorithms that are being tested. So this is what we call direct interference in the paper. Indirect interference is when ranks are stable, but because, like the example, a simple example, because of equilibrium outcomes, you could get interference.
How about I start and then
Yeah.
if there's more questions, there'll be a few minutes after.
So how do I stop? Okay, stop sharing now and you can start.
All right. So thank you very much for inviting me to discuss this paper. It's just a shame we cannot be doing this in person, but it was a very interesting paper. Let me sort of give my version of setting the stage for this. We know that one of the core things that online platforms do is rank and recommend products. And this is a particularly valuable thing for them to do in settings like digital goods, where we have huge product spaces or where consumers have high search costs and they don't have the ability to process a lot of different goods. And so the set of goods you show them is really important. And the way these algorithms are improved is by running experiments. And so these types of experiments are really important for the digital economy and also sort of for the whole economy. But as the authors note, experiments on rankings are different from other types of A/B tests. And in particular, there's this type of interference bias. So the interference bias is the gap between what the demand would be for a particular ranking algorithm if you were to scale it up and use it for, say, 100% of queries, and the observed demand you get in the experiment. And so this, as they note, could be due to things like prices, which respond to the presence of the other algorithms. So you set price as a function of total demand on the platform and not algorithm by algorithm. So if you have different algorithms generating different levels of demand, your price is going to be sort of set suboptimally for any particular algorithm. And this is also true of the other endogenous variables like promotions you might be running or use of advertising or sponsored listings and so on. And of course, this is also true of inventory, as they noted. So then the more direct thing would be if the sales effects from the experimental algorithm is directly affecting the position in a different algorithm. So if you're supposed to be ranked, say 10, and then there's an experiment running, which is ranking you number 1, and you're getting tons of demand from that, that might push you up from 10 to something like 7, 6, 5 in the other algorithm. This might be hurting total demand or total sales if you're sort of being suboptimally placed in that one. I thought this picture demonstrated it very nicely. Here's two different cohorts. So in one, this blue algorithm, the Genesis one, which is the main one, is 60%, and then they switch it up to 80%. And demand in that algorithm, the click-through rate in that algorithm falls. It doesn't stay stable. As you scale it up, the demand falls. All right, even when it's the same for these other two, it's sort of more or less the same for these other two. So I thought this was sort of a compelling picture that this is something people need to be worried about. Okay, so their approach is not to say, well, run different experiments. It's to say, well, we can estimate the bias this is causing, and therefore we can calculate what people need to do to debias their estimates of demand. So they estimate a predictive model of demand, which is a function of hotel characteristics, the position in rankings in each algorithm, and then the discrepancy between those positions. And I put on the slide also endogenous variables, but it turns out that should not be there. So I missed that. And that seems like maybe, we've covered that already, I guess, in the discussion. And then with this model, what they do is they identify the total demand or the true demand effect from the set of observations that have a low discrepancy between the algorithms, either at the hotel level or at the hotel characteristics level. So I thought that Ali described this well, and at the risk of being redundant, I'm going to just sort of repeat it again, because I think if there's one thing you want to take away from this is to understand their method is sort of understanding this identification and not like the nature of the neural nets necessarily. So what you really need are a sufficient number of observations where for a given hotel, there is some cohort, including potentially, I think the focal cohort, where the rank discrepancy across the different algorithms in that cohort at that rank is 0. In other words, there's some cohort up there which sort of looks like 100% of the observations are coming from the same algorithm, in the sense that there's not big discrepancies across algorithms in the rank for that hotel. So that might not occur. There might not be any such cohort, in which case the next step they use would be say, well, if we find similar looking hotels based on their observable characteristics, then we can do a similar thing and say, look, let's see, well, if we can't look within a single hotel, if we have a bunch of hotels and they're all ranked around the same position and they're similar enough, we'd say that's what the demand would be if we were to scale it up. So that's the identification. All right, so with that, they simulate the predicted demand at that point where the discrepancy is equal to 0, and they say that's the true demand. And then they can't exactly test this because there's never an observation where this is scaled up to 100%, but they can compare this to what the simple estimate would be and show that there is, a substantial difference between these. And this bias suggests that the naive interpretation would overestimate demand by quite a bit. All right, so that's my summary, and I have some sort of clarification questions and then some suggestions. My first question was about time. So hotels are different than other products because the hotel room on a given day, eventually disappears when that day goes by. So this generates both dynamic demand and dynamic pricing incentives. And I couldn't tell exactly how these were featured into the model. So for one thing, a query for a given hotel on a given day is going to be different when that day changes. So it seems like the characteristic space is massive if you really account for all these different possibilities. And I also wondered if this would generate a cross-cohort interference as well. So if there was a previous cohort where the hotel is ranked very high, it generates a lot of demand, that demand necessarily has to be lower at a future cohort because there's less availability or because they raise the price because of that. So I couldn't tell exactly what was going on with time. And then as far as I could tell, most of the results focus on measuring the demand for this main algorithm, the Genesis algorithm, but I think it would actually be interesting to discuss these results in the context of the smaller, more novel, presumably, algorithms that are being tested in these different experiments, because you would expect maybe the bias is going to be larger there or maybe smaller, or it seems like this is more what they're trying to measure when they're running these experiments in the first place. And if it's true that the Genesis algorithm is not changing over time, then that's particularly true, that what they're trying to learn from the experiments is about these smaller algorithms. I also kind of wondered if in this empirical application, the Genesis is being changed over time, which it seems like that might be a problem for the model. because presumably the reason they're running the experiments is to learn something and then incorporate that something into their main model. So, and then I thought, like I said before, this plot below is very nice evidence of interference bias. So I was just curious, I think it would be nice to show what sort of the mechanism is here. So if I'm looking at this picture, we have 3 different algorithms in the cohort 15, and they're all doing about the same in terms of demand. And so my guess as the naive person who runs this platform would be, well, I can scale up any one of these algorithms and demand would be more or less the same because they're all about the same here. And then when I scale up the blue one, demand falls for that one. It doesn't change for the other 2. So, you know, it's not clear what's causing that, right? It's not like the demand is dramatically different and then you change the mixture of demands among these and that's going to cause the interference bias. So something else is causing it. So I would be interested to see the same plot just for prices, for instance, and see if when you scale up Genesis, the prices change dramatically, or the use of advertising by some participants changes dramatically, something like that. You know, and I think this data is from, it's 2015, I can see, but you know, maybe this is even more important now as firms use more algorithmic pricing, programmatic advertising. You'd expect the reactions of some of these variables to be larger and faster than they may have been back, you know, 7 years ago. And so both the topic that you're studying is more important now, but some of these mechanisms might have varied us, you know, during that time. Okay, so you know, the next thing, you know, this is me, you know, just coming at this as an economist. There's a lot of assumptions made about the demand model in order to make this work. So for one thing, I think the sort of big one is that the demand for a hotel is just a function of its rank and then its characteristics, including the endogenous ones, which is this variable Sj. But also that conditional on being considered, the purchase probability is still just a function of those things. It doesn't depend on the competitor's characteristics. The endogenous variables also don't respond to the competitor's endogenous variables, and the purchase conditional on consideration, you know, once you get to the consideration stage, the rank sort of drops out of the demand. Okay, so, you know, I think where this might come in is that you say the identification is coming from these places where the discrepancy is 0 across algorithms. But even if discrepancy of 0 is 0, there might be important differences in the ranks of competitors. And so like, say I'm in position 2 in all the different rankings, but some of these rankings put like a very high quality hotel in position 1, and some experiments put a very low quality hotel in position 1. I feel like if I'm going to try to predict my demand in the main case, which is probably where there's a high quality hotel in position 1, that's what I want to sort of scale up. And so it seems like I should care about the rank of the competitors and not just my own rank. Similarly, if we see high demand for a hotel at a low rank, we might want to infer that it has a very high unobserved quality, right? And not just, so not something that's being picked up by the algorithm and not something that's part of the set of observable characteristics, or vice versa, if we see a high ranked hotel getting low demand. Similarly, if I am a person, or is it a consumer, purchased from a low ranked hotel, it probably means I have a high match value for it. And so there's going to be some selection into the consideration set on that match value that generates a kind of a selection bias. So, you know, I'm not sure what to do about this. I understand these assumptions are kind of standard in the computer science or operations literature, but like, as you know, coming from the economics point of view, I would say it would be worth at least trying like a simple simulation, maybe with a random utility model, some search costs and equilibrium prices set under each algorithm to show maybe these are not that important of factors. And that's plausibly true. And I know that most of the changes in these algorithms are relatively small, but I would say, you know, I would guess that the set of hotels in the consideration set are going to generate different demand effects. And some of these competitor issues might matter. So I don't think you want to estimate this model, but I think you might want to like write down a simple version of it simulated. Just to, that would sort of convince me this is not something you need to worry about. All right, and then the last thing is that, you know, I think it's really nice that you can estimate this model on the existing set of A/B tests. So this doesn't say you have to change the experiments that need to be run, but I think it would also add to the paper if you were to push a little out on what are the implications for how they should change tests going forward in order to take advantage of this. So you do know in the paper, I like this, that you say you need to run a lot of more tests that have more variation. And presumably, I think that's to increase the number of observations where you have low rank discrepancy across the set of cohorts. So I think that's a good one. Although I wonder if that comes at the cost of learning. If you have lots of that, it means maybe your experiments are not learning as quickly because there's relatively little changes going on. And similarly, you know, I was thinking as a whole, this approach by relying on this rank discrepancy issue might mainly apply to sort of small incremental changes in the algorithm. We might want to occasionally try like very radical changes to the algorithm, in which case I think that this debiasing approach would be less applicable. You know, one way to think about the implications of this might be to say, and this is probably a second paper, a follow-up paper, but like, would there be an optimal way to structure the way these rank discrepancy observations are placed in the algorithms across cohorts so that you can learn the most from them? And I think this would be especially true if it could be done in an adaptive way, because presumably, you know, they don't want to run 16 experiments for a full year and then sit down and analyze them and say, okay, now what do we learn? I think they want to learn at every iteration. And so just sort of saying, what do we learn at iteration? How do we change the next experiment to get the most out of it? I think that would be great. And again, I think that's a follow-up paper, but I think that would be really interesting. All right, and anything else, you know, you might think of for talking about the implications, I think would be really useful for people. So I don't want to give the impression I'm sort of nitpicking a little bit here, but I think this is a really important topic. These types of experiments are super important. And I think that this has already made a really substantial contribution to that topic. So well done.
Thank you, Brett. Just a couple of points. So regarding the seasonality features, they capture sort of consumer heterogeneity in the following way. So we basically look at destinations, okay? So the idea is that if in some season people are looking for Barcelona, it's a different season than when they're looking for London, and then New York. So the composition of queries is then distilled into a representation vector, which sort of captures what type of customer is sort of arriving on the platform average. It turns out that it's doing a good job, especially out of sample, but we can certainly, you know, include more. I actually have included more. They don't seem to, like, you know, if they're traveling with the kids, stuff like that, whether this season, you know, is a season where you take family vacations, stuff like that, they don't contribute much more on top of this. So that's one. You're absolutely right. You know, there's no free lunch. It has assumptions. And these are, you know, as you mentioned, these are pretty common assumptions on CS and OR side. And the reason you need these assumptions is that you need to be able to decouple this at hotel level. Otherwise, you know, you have to see who are your competitors. This ranking discrepancy is now not only matters for you, but also your competitors. It seems like, at least in our application, when you aggregate it, even if there's some errors, some of it washes away. Okay, it's doing a good job, but I agree that it has limitations there. Also, regarding the simulation, you can put the data in process, see if you can back out, you know, what would have happened. There, that's certainly doable. What else did you mention? There was another. Oh, so regarding the mechanism, we were also very interested. The reason is that mechanism can actually change even across cohorts, right? So looking at prices, it could be that it's coming from prices or a host of different issues. The fact that the ranking algorithm itself can have features, as you mentioned, it can have overall sales. This means that competition changes, the number of impressions that a hotel gets is going to change. Okay. Now that by itself, you're showing it to more people. CTR can change because now different types of people are going to see it, right? So that is an issue. That's why we didn't really look at the mechanism. It's agnostic to the mechanism. And that's why we don't include prices. Because if you put prices, now you have a model that should predict prices indeed in the counterfactual. Now you're basically committing that it's the prices that is causing it, right? So we try to keep it fairly agnostic there. But these are very good. Thank you very much. I'll try to look at these avenues and try to improve that. But it's certainly difficult. It happens a lot. I have seen it happening in other contexts as well, other data sets as well. So there must be a way to sort of, address it. I think the next paper is starting right now. Thank you very much again. Thanks.
All right. Can I get started?
Yes, you can start.
All right. Hello, everyone. I'm Jason from Rutgers, and I'm very excited to share my work with you today. So I'd like to begin by thanking the conference organizers for selecting our paper to the program. This is a joint work with Amin Saidi, who is here with us today. And we are currently revising the paper, so any feedback or questions would be extremely helpful for us at this stage. So please keep those questions coming. Please feel free to interrupt me or leave questions on the chat. So what is this paper about? This paper is about the introduction of a new ad transaction platform and its effects on the display ad market. And to make sure that everyone here is on the same page, what I'm going to do first is provide a quick overview of this display ad industry, like who the buyers are, sellers are, how transactions occur, and then I'll talk more deeply about the emergence of private exchanges. So the display ad market can be broken down into two submarkets. The first is direct transactions, and this accounts for approximately 75% of the display ad market. And what happens here in direct deals is advertisers like Toyota and publishers like Financial Times, they directly negotiate how many impressions of Toyota's ads to display on Financial Times and at what price. The second and relatively newer category is real-time bidding, or RTB for short. And as the name suggests, in contrast to direct deals, where the terms of the deal were pre-negotiated, in RTB transactions occur in real time. So as a consumer arrives on the Financial Times, an auction takes place. Advertisers submit bids in real time, and the advertiser with the highest bid will win the auction and have its ads shown on Financial Times. And our paper is about RTB. And within this RTB transaction format, we're going to look at the different ad exchanges and how what it means for this whole market. So let's delve a bit deeper into the mechanics of an RTB transaction. I'm sure many of you are already familiar with this, so I'll be relatively brief here. So again, suppose a consumer arrives on the financialtimes.com. That triggers Financial Times to send a call out, including the consumer and website information, as well as reserve prices for the auction. The ad exchange then sends that call out to the advertisers participating in the exchange. And for the sake of illustration, let's suppose there are Coke, Pepsi, and Toyota, 3 advertisers. So the 3 advertisers receive this call out and they respond to this bid request by sending their ad copies as well as the bids. So you can think of these as the maximum willingness to pay for showing their ads on Financial Times. And by the way, this is amounts per 1,000 impressions. So Coke is willing to pay $2 for 1,000 impressions shown to this consumer. Pepsi bids $2.5. Toyota bids $1.5. So in this case, the winner is Pepsi because it was the highest bidder, and the price that Pepsi will pay for the 1,000 ad impressions will be $2.5. Pepsi's ad copy will be sent to financialtimes.com as well as the payment of $2.5. Although in practice, a lot of that would be split between intermediaries within that arrow there. Okay. And the consumer finally sees the content as well as the ad that is served by Pepsi. And all of this process takes less than 100 milliseconds, and hence the name real-time bidding. So this type of ad exchange where kind of any advertisers and publishers can transact is called an open exchange. And this openness can be both a good thing and a bad thing for publishers like Financial Times. First, it's good because for any given ad impression, the openness ensures a sufficiently large number of bidders. But on the other hand, the openness can also be a bad thing because it makes the exchange vulnerable to fraud. So for example, fraudsters, what they can do is they would mimic the call out from financialtimes.com and deceive advertisers into spending ad dollars on their fake impressions. Okay. In fact, this is not a hypothetical example. Financial Times was one of the many publishers that was subject to a huge ad fraud. So here's an interesting anecdote from Wall Street Journal 5 years ago. Okay. So what happened was Financial Times, they wanted to assess the degree to which they were being subjected to these fraud issues. So what they did was they tried buying their own ad inventory in open exchanges. Okay, so they tried to buy their own inventory, and what they found was that there were 300 fake accounts under the guise of Financial Times selling fake inventory. Okay, and the magnitude is quite staggering. So approximately $1.3 million worth of FT.com space was sold in each month. Okay, so you can see how large this issue is. And so this illustrates how severe this ad fraud issue is about 5 years ago. And you may wonder, okay, has the situation improved since then? Has the system caught up with this issue and policed it? Unfortunately, the answer is not so much. If you look at the bar graph on the left, it shows the percentage of ad impressions that were categorized as being fake. Okay, so if you look at the top, in India, about 40% of ad impressions that were transacted were categorized as being fake. So this is from the time period of April 2018 to April 2019. And in the middle, you can see United States is also pretty high, 20%. So 1 in every 5 ad impressions are categorized as being fake. Now, if you translate these numbers into dollar amounts, as you can see on the slide, according to Juniper Research, US advertisers are expected to lose about $23 billion to ad fraud this year. So again, a huge issue. This raises the important question. So what is the solution? How is the market coping with this issue? One trend that has emerged in the RTB industry in response to fraud is the growth of what's called private exchanges, also known as private marketplaces. So what is a private exchange? You can think of private exchanges as kind of an exclusive club. So you have reputable publishers or a single publisher who offer their ad inventory to only a pre-selected group of advertisers on an invite basis. Okay. And so if you look at the chart on the left, the red bar denotes the ad spending in US that was going to private exchanges, and the black bar is ad spend on open exchanges. And you can see that by 2021, that was the tipping point where the majority of more ad spend was going to private exchanges than to OX. And that trend is sort of magnifying, is projected to magnify until 2023. Okay, so private exchanges has emerged. And so from a kind of high level perspective, you might think that, okay, private exchanges, great. You might think that they're just like a screening mechanism. They're providing a screening mechanism to separate good impressions from the fake ones. But interestingly, we find that it's much more than that. And the reason it's much more is due to the exclusivity factor of private exchanges. Okay? So what we find is that the exclusivity of private exchanges adds a nuanced strategic layer to the picture. Okay? And the goal of my presentation today is to tell you guys about this novel strategic interaction arising from the adoption of private exchanges. So to quickly summarize, the fraud is a very prevalent and important issue in open exchanges. And so private exchanges have emerged as a sort of alternative to remedy this problem. And the key feature I want you guys to have in mind throughout the talk is that PX is very exclusive. Only a pre-selected group of advertisers can transact with reputable publishers. And the main focus of this paper is going to be how will PX impact the display ad market? Any questions before I go on?
Yeah, quick question.
Yeah, Ram.
Do advertisers do any monitoring at all? I mean, it seems to me that a lot of contracts, usually are monitored. So here, there's no possibility of monitoring, or
They are monitoring, but it's not very successful. So it's a constant kind of cat and mouse chase. So once they are able to successfully detect fraud, the fraudsters, they again find a way to game the system, and fraud continues. They keep buying bad inventory, and there's also a huge business of third-party auditors who are trying to help advertisers monitor these bad impressions. But even there's like huge measurement errors. One agency says categorizes certain impressions as fake, some don't. So there's a huge uncertainty in this area, and it's still an ongoing
is there any scope for the whoever is getting paid for this, the publisher, using cryptocurrency to get rid of this whole problem? Because other people, then you can only access it if you're eligible to do it. It's sort of like private exchange, but it's not quite.
Right.
Just a thought. That's all.
Yeah, that's an interesting thought, and it's also possible that this this blockchain technology can also be used as a way to kind of ensure verifiability of transactions. So I think that kind of technology is emerging. I haven't seen it fully scaled so far, but I think the market is opening up to that kind of technology too. So yeah, great thought there.
Thank you.
Thank you, Ram. All right, so what are we interested in? We're interested in the following questions. How does the emergence of PX affect the advertiser strategies and their payoffs? And also, how does it affect the publisher, the Financial Times, selling mechanism? Should it sell its ad inventory through PX, OX, or both exchanges, and at what prices? Okay. We're going to look at the selling mechanism as well. And also, finally, we'll look at open exchanges incentive, or lack thereof, to fight advertising fraud. So that's the agenda. And let me give you a quick preview of the main results. So we identified two main effects of introducing PX to the display ad market. And the first is the kind of intuitive direct effect. And that is that private exchanges help filter out for advertisers fake impressions. And so this alleviates advertisers' fraud concerns, thereby increasing the market efficiency. So that's a good thing, both for all players in the system. The second and indirect effect, which is the main result of our paper, is that by virtue of their exclusivity, private exchanges, what they do is they create an information asymmetry between advertisers that have access to PX and advertisers that do not have access to PX. Okay. So advertisers that are connected to PX know that the impressions that are coming through PX are legitimate, while those who are not connected may have less information about the legitimacy of these impressions. So what this means is now the connected advertisers will bid selectively higher for the good impressions, and this leaves a higher chance of the unconnected advertisers ending up with fake impressions. So this means the unconnected advertiser lowers their valuation on average, and therefore this in turn softens the bidding competition. And interestingly, the publisher can actually be worse off by introducing PX than the case when they did not introduce PX. Okay, so I'll walk you through this mechanism in more detail later, but that's sort of a, high level result that we find. We also find that private exchanges, they can also have this effect of regulating the market. And what I mean is it creates competitive pressure that can motivate open exchanges to fight fraud. Whereas without private exchange, open exchanges would have had less incentive to self-regulate and fight fraud. So these are the results that I will be going through. there's a large body of research on online advertising auctions and display ad. I'll just quickly mention here that the key contribution of our paper is that we look at the effects of different exchange formats, namely private exchange and open exchange. And in particular, we uncover a novel information distortion effect induced by the exclusivity of exchanges that only provide access to a subset of advertisers. And I'll again tell you more about that later in the coming slides. So we construct a very simple stylized model as follows. So we have nature that is generating an impression from the fraudster with probability beta, and with probability 1 minus beta, the impression is drawn from a legitimate publisher. Think of Financial Times. So beta is the measure of kind of baseline fraud intensity in the system. The higher the beta, the more likely an impression coming through open exchange is likely to be fraudulent. Nature also decides whether each advertiser has high evaluation for the ad slot or low evaluation. That's going to be measured by probability mu. And here are the advertisers' valuations. So there are 2 advertisers, and these are symmetric, except for their access to private exchanges. And what you should remember here is that an advertiser values an ad slot only under 2 conditions. If the advertiser has high valuation and the ad slot turns out to be legitimate. Okay? In all other cases, the advertiser, for simplicity, we assume has 0 valuation. Advertiser I submits bid B sub I, and if that advertiser wins, its total surplus or profit would be its valuation minus the bid that it submitted. Okay? So this is a first price auction. We have one publisher, the Financial Times, that sells through exchanges and first price auctions. And its main decision is to set reserve prices, RO for OX and RP for PX. Okay? And just a small technical note here. Note that if, for example, RO equals infinity, that's equivalent to only selling through PX. So you can think of RO and RP determining both the price and the choice of exchanges. All right. What is the publisher's revenue? If the maximum bid that it receives exceeds the reserve price that it set, then that would be the revenue. Otherwise, there's no winner in the auction and the publisher makes 0 revenue. So here's a visual description of what's going on. So on the left-hand side, you have 2 advertisers. They can bid in the open exchange, but in the open exchange, it's also exposed to fraud risks. So you have the fraudster mimicking the publisher. The publisher is represented with green throughout the presentation and fraudster with red. And again, I want to emphasize that in the open exchange, an ad impression is fake with probability beta. And one of our main objects of interest is how does introducing PX affect the whole picture? So we're going to look at PX, which provides exclusive access to advertiser 2. Okay? And just so we're all clear, private exchange is run by the publisher. Okay? So the publisher sets reserve price in private exchange and in open exchange. And advertiser 1 does not have access to PX, while advertiser 2 does. So we'll refer to the advertiser 2 as being connected to PX and advertiser 1 as unconnected. And in private exchange, impression is never fake because it is able to successfully screen out these fraudsters from sending their bid requests through PX.
Hi, Jason, a very quick question. So for the previous slide, if the low value has a, say, smaller value than 1, how does it change the result? Because here is 0, so it's the same as the fake.
Yeah, it will not change qualitatively.
Okay.
Yeah, that's all I can say, really. The
Thanks.
math is just more complicated, but qualitatively, it'll be basically.
Sounds good.
All right, what's the timing? So first, the publisher will set the reserve price. So at the bottom right, you see publishers setting the reserve prices for open exchange and private exchange. Nature draws ad impression from the publisher or the fraudster. Advertisers bid in the first price auction. And again, emphasis here being that advertiser 1 can only bid in OX, but advertiser 2 can bid in both exchanges. Auction outcomes and the payoffs are realized. The publisher receives the clearing prices from each of the exchanges and selects the exchange with the higher clearing price. The important point to note and remember throughout the presentation is the information asymmetry here. The connected advertiser, the blue advertiser, knows the impression source in PX. So if it sees an impression bid request coming through PX, it knows that it's a good impression. But in the open exchange, it does not know whether the impression is good or not. The unconnected advertiser, who only has access to OX, does not know whether the bid request coming through OX is legitimate or fake. Okay, so we're going to solve for the sub-imperfect equilibrium, but before we do that, we're first going to look at two simple benchmarks that will help elucidate the pros and cons of each exchange type. So what's the pros and cons of OX, and what are the pros and cons of PX? Well, first, let's look at the case where there is no PX, such that all transactions occur through OX. So the question here is when an advertiser, either advertiser 1 or 2, sees a bid request coming through OX, how much is it willing to bid? Or equivalently, how much is their valuation? So in this case, the high value advertiser's expected valuation is going to be 1 minus beta, because that's the probability of the impression being legitimate. So what the publisher does, it sets the reserve price as high as the willingness to pay, and thereby extracts everything in expectation. And advertisers with probability mu, which is the probability that they draw a high valuation, will bid exactly that amount. And so their surplus would be completely extracted by the publisher in this case. The auction takes place, and the highest bidder wins, and the publisher's expected revenue is the formula given on the slide. The takeaway from the OX only regime is that it ensures a thick market because it's open to all types of advertisers, but the valuation of the advertisers in the open exchange may be lower because of fraud risks. Okay. So simple trade-off. Whereas in the PX only regime, it's a reversed trade-off. So there's only one advertiser who is connected to PX. So its valuation for a bid request coming through PX will be 1. That's exactly how much the publisher will set the reserve price. Advertiser bids that amount, and the expected revenue would be mu, which is the probability advertiser 2 draws a high valuation. And again, in contrast to the OX only case, the trade-off here is the market is thinner in private exchange due to the exclusivity, but advertisers have higher valuations in private exchange because of the mitigation of fraud risks. So you can see that each exchange has their pros and cons, and this raises the question, so what would be the optimal strategy for the publisher to sell its ad inventory? And you may wonder, if it sells through both PX and OX simultaneously, would that mean the best of both worlds? So thick markets from OX, as well as a high valuation in PX. So is that always going to be the optimal strategy for the publisher? The answer is going to be no. Sometimes yes, but sometimes no. And that sometimes no case is the more interesting case. And that's going to be one of the main insights of this paper. So is PX OX, is the regime in which the publisher sells through both PX and OX the best of both worlds? Yes and no. So the pros is PX mitigates fraud and OX expands the bidding pool, so that's good. But there are strategic ramifications, these are the cons, as a result of selling through both exchanges. So I'll go through these slowly because this is the most important slide of the talk. So we call this the devaluation effect, and I really invite you to think through with me here. what happens is if the publisher sells through both PX and OX, the connected advertiser, by virtue of their connection to the private exchange, can identify legitimate impressions, whereas the unconnected advertisers cannot. So what the connected advertiser does is it has the luxury of, it can exploit the information to bid high for a legitimate impression in PX and bid nothing in the OX. And what that implies for the unconnected advertiser is that now, from the unconnected advertiser perspective, I'm facing a much more informationally advantaged advertiser. So I'm more likely to end up winning fake impressions because the good ones are more likely to be poached or sniped away by the connected advertiser through PX. So again, under the PX-OX regime, the unconnected advertiser has a higher chance of winning fake impressions compared to the OX-only regime. So compared to the regime where all advertisers were equally uninformed. And therefore, the unconnected advertiser lowers their valuation for impressions coming through OX, and therefore bids lower. But the story doesn't stop there, right? Because if the unconnected advertiser lowers its bid, the connected advertiser can respond by lowering its own bid too, because it now faces a softer competition. So overall, from Financial Times' perspective, by selling through PX and OX, it creates this information asymmetry that reduces bidding competition, and therefore the Financial Times can end up being worse off than selling through, for example, OX only. Okay. So that's the main devaluation effect that we find. So to repeat what I just said very quickly, even if the intensity of baseline fraud is fixed, the mere fact that the connected advertisers are informationally advantaged by virtue of their access to PX, this lowers the unconnected advertiser's bid, and therefore the bidding competition is softened. So that was the kind of high-level intuition explanation. Now what I'm going to do is kind of get into the mechanism behind the devaluation effect. And I invite you to think through these numbers in the tables with me. So for this slide, we're thinking from the perspective of the unconnected advertiser. Okay, the unconnected advertiser that has high valuation. And the numbers, you see two numbers here, 1 and 0. These indicate the probability of the advertisers winning the ad impression under each regime. So the top table is going to be the probability of advertisers winning an impression in the OX-only regime. And you can see that when the high-value unconnected advertiser faces a low-value connected advertiser, it always wins because the connected advertiser with low valuation will not bid for the impression. And that's the same regardless of the regime, whether it's OX-only regime or PX-OX regime at the bottom. The high-value U advertiser always wins. But now things get more interesting if you look at the high-value connected advertiser. Okay? So when the high-value unconnected advertiser is facing a high-value connected advertiser, the probability of winning in the OX-only regime is half because they're equally uninformed and they share the risk of ending up with, share the probability of winning, basically. But in the bottom table, if you look, compare the left and right tables, the connected advertiser with the high value will win legitimate impressions for sure, and the unconnected advertiser with high valuation will win fake impressions for sure. And that's because of the information asymmetry, again, that is induced by the private exchange. And this is the source of the devaluation effect that I mentioned earlier.
Hey, Jason.
Hi, Faye.
Hey, how are you? So a question about the timing. Is a publisher sell the same impression at both OX and PX at the same time? Or OX first and PX, or PX first and OX, or this is an option for the publisher too?
Very good. In the main model, it is simultaneous selling. But even if we allow the publisher to sell first through PX and then through OX, the results carry over. And if you think about it, it's clear because what matters is the unconnected advertiser being disadvantaged, or to put it differently, the connected advertiser being prioritized. So if the good impressions are sold first through PX, then that actually magnifies the, if you like, the premium or the preferential treatment given to connected advertisers. And therefore, this actually amplifies the devaluation effect. Unconnected advertisers under sequential selling, they're actually kind of worse off. So they even dampen their bids even more. Does that make sense?
Yeah, thank you.
Okay. All right, so we found that if the publisher sells through both PX and OX, there's this devaluation effect. The next question is, so what's the optimal exchange configuration? So under what conditions should Financial Times sell exclusively through PX, exclusively through OX, or through both exchanges? And to answer this question, we need to first understand how the devaluation effect varies by the model parameters. Okay? And to refresh your memories, the two model parameters are mu and beta. So mu was the probability of the advertiser drawing a high valuation, and beta was the baseline fraud in the system. Okay? So depending on these parameters, when does the publisher choose what type of exchange configuration? So to get a sense of how devaluation effect varies by mu, we're first going to look at this plot here. So the x-axis is mu, the probability of the advertiser drawing high valuation, or it can also be thought of as average ad valuation. And the y-axis is the unconnected advertiser's bid in OX. The beta is fixed at 30%, somewhat consistent with the motivating examples from the introduction slide. Excuse me. The solid line is the unconnected advertiser's bid in the OX only regime. So this is 1 minus beta, so it'll be 0.7. And the dashed line is the unconnected advertiser's bid in the PX OX regime. And you can see that it's lower than the solid line. So this is reflecting the devaluation effect, as I drew on the slide there. And you can see that as mu increases, the devaluation effect amplifies. So what's going on here? From the unconnected advertiser's perspective, the information asymmetry effect really kicks in only when it's facing a high value connected advertiser. So if the probability of the unconnected advertiser facing a high value connected advertiser increases, then the unconnected advertiser anticipates, hey, it's much more likely for me to end up with fake impressions because the high valuation connected advertiser is going to take away all those good apples. So the devaluation effect increases with mu. And it's what more do I want to say here? Yeah, so the devaluation effect makes selling through both PX and OX not a very attractive option for the publisher. Now, there's another much more familiar force that makes PX/OX less attractive, and that's, of course, the cannibalization effect. The fact that Financial Times offers both OX and PX, if OX becomes sufficiently attractive, then that would cannibalize the surplus from it can extract from the private exchange. So the fact that the connected advertiser has access to both PX and OX can create this cannibalization effect. And this is even more amplified. This interacts with the devaluation effect, because now what happens is the devaluation effect lowers the unconnected advertiser's bid, and therefore the OX reserve price has to go lower, but that makes bidding in OX more attractive for the connected advertiser. So the publisher, in response, has to also commensurately lower the reserve price in the private exchange. Okay? So lower prices in OX due to devaluation implies lower prices in PX due to cannibalization. It's kind of like a double whammy situation. Here's another plot that shows the interaction of cannibalization and devaluation effects. And basically the connected advertiser, compared to the case where compared to the regime where there's only the PX as a transaction platform, the connected advertiser lowers its bid. Okay. And another takeaway from this plot is that as beta increases, the devaluation effect increases. So the bids are going lower and lower as beta increases. Okay, so now that we have delineated the key forces associated with the various exchange configurations, what we're going to do next is characterize the publisher's optimal exchange choice. And interestingly, what we find is that all three types of exchanges are possible in equilibrium. So let me break this down for you, what's going on here. So on the x-axis, we have the fraud intensity, the baseline fraud intensity in the system. And on the y-axis, we have the average ad valuation mu. As you can see, so all three types of exchange configurations may arise. And let me first tell you what's happening as beta increases. So as the plot goes from left to the right, you see PX only emerging as the equilibrium configuration. And that's because as beta increases, OX becomes increasingly bad, and therefore the publisher has to correspondingly lower the price in PX to make up for to prevent connected advertisers from switching from PX to OX. But because of this cannibalization, the publisher just says, hey, I'm just going to throw away OX and sell exclusively to PX at a high margin. So if fraud is very high, the publisher will sell exclusively through PX. Now let's look at mu. Let's fix beta and take mu going from 0 to 1. You can see that as average ad valuation increases, remember that plot where the devaluation effect amplifies with mu. So remember the devaluation effect is operative in the PX-OX regime, the bottom regime on the plot here. So to counter that devaluation effect, what the publisher does is, hey, this information asymmetry is really softening this bid competition. I'm going to remove this asymmetry between advertisers. And the publisher can do that by either going OX only or going PX only. So that's what we see on the plot here. Okay. Now we arrive at the last part of the presentation, and that is, so what does all this mean for the open exchange? So until now, we've kind of treated the open exchange as a passive agent, but in some sense, it has, to some extent, it has control over the types of impressions that it lets through. Okay, so let's look at how PX impacts OX's profit first, and then we'll look at OX's incentive to maybe fight fraud on its own. So first, we find that the introduction of PX hurts OX's revenue, and the hurting occurs through two distinct ways. So if you first look at the right region, the top right, the publisher sells exclusively through PX. So this induces a separation of good impressions being sold through PX and bad impressions being sold through OX. And therefore, advertisers who otherwise would have bid in OX no longer bid in OX. So the separation reduces the transaction volume in OX. So that's one way in which PX hurts OX. The other way in which PX hurts OX is the devaluation effect, right? So because of PX, advertisers are informationally advantaged and disadvantaged, and this softens the bidding competition. And so the willingness to pay in OX decreases. So to summarize, because of the devaluation effect, introducing PX may reduce OX's margin per transaction. So the first top right corner is about PX reducing volume. The bottom regime is PX reducing margin, as well as transaction volume because of PX. Okay, so again, this brings us to the last question of the talk, which is what should OX do in response to these negative effects of PX. So sort of going back to Ram's earlier point, one approach is for OX to help advertisers avoid these fake impressions by deploying fraud detection tools, as well as kind of pre-screening for potentially fraudulent impressions. And this is exactly what Xandr did, one of the biggest exchanges, back in 2015 when it launched an anti-fraud initiative called Inventory Quality. Okay? And so just in a nutshell, what they did was during the 6 months project, they purged about 80% of impressions that were sold through their exchange. So this was a way to counter fraudulent impressions being sold.
Jason, you have 5 minutes.
Okay, thank you. But if you look at the top region, fighting fraud may not always be in the OX's interest. Why is that? The reason is that Open Exchange's revenue model is based on commission. So for every transaction, whether it's legitimate or fraudulent, they take a cut. So if they reduce fraud, that could mean lower transaction volume, and therefore the OX's profit overall could decline. So in this case, if mu is very large, OX has less incentive to fight fraud. And I just cited a small article here that shows exactly that phenomenon, where the players in the system don't solve the fraud issue because they don't want to. The incentive is so perversely aligned that they want to keep bad impressions being transacted. All right. Very quickly, going back to Faye's question, we have an extension with sequential bid request. So instead of the publisher selling through both PX and OX simultaneously, what would change or not change if the publisher sent bid requests first through PX and then through OX? And as I explained to Faye earlier, this has the effect of magnifying the devaluation effect because it even more prioritizes and gives preferential treatment to the connected advertiser, which means the unconnected advertiser will anticipate even higher probability of ending up with fake impressions. We also look at another way in which OX can be active instead of fighting fraud. So what if the Open Exchange can endogenously set the commission rate for the transactions that occur? And we find basically that the main qualitative insights carry over. The only thing that changes is in the region where the publisher sold through OX only, sometimes OX would rather induce PX OX regime than OX only regime. So just a couple of robustness checks, and let me summarize and end. So ad fraud is a major issue, and it has motivated publishers to sell through private exchanges as a partial kind of remedy to this issue. And this paper studies how the emergence of PX affects the display ad market. And the key finding of our paper is that PX can be both a blessing and a curse for publishers like Financial Times. So it can be a blessing because of this fraud filter effect. So this raises the connected advertisers' valuations, but at the same time, it can also induce an information asymmetry, which lowers advertisers' valuations that softens bidding competition. So overall, it could be a bad thing for publishers. And finally, we found that the competition created by private exchanges can motivate open exchanges to fight fraud. So here are some takeaways for managers and for policy makers. So for publishers, they should be, before kind of rushing to implement these private exchanges and setting up and transacting through private exchanges, they should be mindful of these information asymmetry effects that the exclusivity of PX creates. And for unconnected advertisers, they should bid lower in OX if the publisher is known to offer PX as well. And this is because of the devaluation effect. Finally, for policymakers, in the last 30 seconds, having PX in the system can increase ad allocation efficiency. But what's interesting is that if you let publishers B, then PX may not arise in equilibrium. Okay? This was because of the devaluation effect. And therefore, some kind of regulatory intervention may be needed in these conditions to help the market self-regulate and fight fraud on their own. So, oh, I missed a lot of chat. My bad. And I'm out of time, so I think I'll stop there.
Hi, everyone. Can you see the slides?
Yes.
Yes.
Right, thanks. I'm Chi-Hong Liu from University of Oklahoma. I first want to thank the conference organizers for inviting me to discuss this paper. Let me start with a quick summary of the paper. I probably wouldn't do justice to the paper because Jason has just spent 40 minutes to present his paper. So I want to sort of give a quick overview first to give my impression of what I think is the strength of the paper, and also to pivot that to my comments. So it talks about fraud, and fraud has been a major issue in digital advertising. If you're concerned with ad effectiveness, then fraud brings a whole new meaning of ad effectiveness. And you can also think about fraud as capturing other dimensions such as fake news, misinformation, and so on. And the setup there is a little bit different because in the fake news and misinformation case, the ad gets real exposure, and the ad exchange also get real dollars, but the negative consequences probably in other dimensions such as bad API and so on. So maybe the insights from this paper can shed light on the other problems, in those situations. But of course, with fraud, market participants will develop ways to cope with fraud. And this paper focuses on this specific one, publish organized private exchange, and see how it interacts with open exchange. A natural question is how the introduction of this private exchange affects the equilibrium. And given the size of the market, there's a lot at stake. So the very nice stylized model with access asymmetry, two advertisers. One connected advertiser can access both open and private exchanges, but the unconnected advertiser can only access the open exchange. Now, without the private exchange, when there's only an open exchange, the fraud ads are shared by both advertisers. Now, with this addition of private exchange, and the collected advertiser is going to bid through the private exchange to avoid the fraud. And without the fraud, the collected advertisers who needs to pay increases, and so does the bid. And now, if you look at the uncollected advertiser, the uncollected advertiser only bids through the open exchange. And the open exchange now is where the fraud is. And now the collected advertiser is not here anymore. So all the fraud will fall on the uncollected ones. So the uncollected advertiser bid will go down. And this is what Jason and Amin called a devaluation effect. At the same time, because the uncollected advertiser bids goes down, and the collected advertiser also bids goes down because this is the dampening competition effect. So if we zero in this a little bit closer, and we can see this kind of asymmetry here in the sense that private exchange hurts the advertiser, the uncollected advertiser. And this also in turn hurts the publisher because the uncollected advertiser bids goes down. On the other hand, the private exchange benefits the collected advertiser. But the publisher is unable to extract the increase in surplus. So the collected advertiser, even though I have a high willingness to pay, but I don't have to bid higher because now I'm competing against a weaker rival, right? So the model does have a channel where the publisher can adjust reservation prices, but this may not be enough. And this is why the private exchange potentially can hurt the publisher. So the first thing here is this asymmetry between the gain and the extraction. So the collected advertiser gains, but then publisher does not necessarily have the ability to extract that increase in surplus. So this is also where my first comments is about. Okay. So overall, I think this paper addresses very important question, well motivated with strong practical relevance. What I like most about the paper is it uses a clean, stylized model. It's very clear on what it's trying to find and deliver very cleanly and convincingly, and using the, capturing the key features and trade-offs. The results were some surprising in the beginning, but after I read through the explanations, I think it's very sensible. The paper is very well written. And I think this is the first paper that I know look at private exchange, how it affects open exchange. And I feel like this opens up a new research area and potentially inspires a lot of extra work in this area. I will be interested in pursuing this myself. And I'm going to try to list some of these potential ideas. And some of them, Jason and Naveen has already done in the extensions. Okay. So I'm going to start with this first thing of asymmetry by extracting surplus. So right now in the paper, the reservation prices is the publisher's instrument to extract the surplus. This plays a very important role. And I have a little bit, Jason and I here a little bit disagree a little bit. And I understand reservation price is commonly used, but the reservation price in this model has a very specific role in the sense that the reservation price by the publishers and the bids by the advertisers are best response to each other. So that means that advertisers need to calculate what the reservation price is and take that into account. And then the publisher needs to take further that into account to decide how to determine reservation price. Now, in the real-time bidding case, I would kind of think that ad slots like a perishable goods, right? You either sell it or lose it. So I'm thinking of like reservation prices. Say, okay, if I sell this ad, what is the cost to my viewers, right? So I want to at least get that back. So I'm more like open to reservation price to sort of reflect that cost of introducing an ad, but not so much as to extract surplus. Okay, so this is especially important for programming bids, right? And this, of course, is potentially costly for advertisers to calculate the almost optimal reservation price. I think Ram has talked about questions about monitoring. The things that those bids, these auctions happen so, each auction is worth only a few cents. I think it's very, very difficult to monitor. It's too easy to cheat and it's too costly to monitor. So I think to some extent, I think the reservation price, the way it's been modeled here has a flavor of that as well. It's going to be difficult to do. So I'm thinking about a couple of other dimensions to extract surplus. One is price discrimination, loosely speaking. Basically, that you can handicap the bid from the private exchange, right? And I think this may be implementability and scalability may be reasonable because now you're just treating two different platforms. You can have some broad measures of, okay, if it comes from the open exchange, what do I accept? And it comes to the private one, how much do I accept? So basically just to handicap it. So force the collected advertiser to bid a little bit higher, right? Another one here, I'm not sure how much role it plays now. The collected advisor bids through the PX, but also retains the option to bid through the open exchange. And on the open exchange, and the platform cannot distinguish, the publisher cannot distinguish between the two advertisers. So this really limits the publisher's ability to extract surplus. So one thing one can think about this, I don't know whether it actually would be relevant in the equilibrium, maybe it wouldn't change a thing, but it's possible that a publisher can impose some kind of exclusivity constraint and saying that, each advertiser, you can only bid through one exchange, right? So the collected one, if you want to bid through the private one, you can only bid through the private one. So that would reduce the collected advertiser outside option and in turn increase the ability to extract the surplus. Okay, right. So that's my sort of major comment of the paper, and then I have a couple of comments on the some of the features of the model. I have to say that one thing I like about the model is that it's clean, and the things I'm saying, if you do pursue it, it's probably not going to be as clean, right? So maybe just some discussions about offer some insights. Now in the current model, the ad slot is generated first, and with the exhaustive probability of the ad being fake or real. So in this model, you have positive probability that the publisher will never send an ad, never send a request for bid. That in the equilibrium, it doesn't seem to wouldn't be. I doubt that would be supported as equilibrium feature. because if you have a real ad, I would always sell it, okay? But it's also how to model the alternative. Because suppose now that the real ad is always there, and they also have the real ad slot plus the possible fraudulent ad slot. Now I have at least 2 ad slots. But then the unclicked advertiser can use the number of ad slots to infer, okay? And that's gonna change a lot because now this potentially becomes some kind of signaling problem as well. And this will complicate analysis at the cost of the strength of the paper, which I think is very clean and focused. And then the other one is that, it seems to me that the fraud comes from the side that's trying to receive the money, not the side trying to pay. So it's a little bit hard for me to see why you want to limit the number of advertisers, unless you have some kind of skills, right? I want to have big publishers to work with big advertisers, maybe some kind of transaction cost, which is not a model in this paper, right? But otherwise, I would to still have, so the private exchange would have all the advertisers, right? So the paper right now motivates advertiser side restriction with the idea such that in the private exchange, you can potentially provide more information with advertisers. So this gives you a flavor of advertiser heterogeneity. Some you want to invite, some you don't want to, okay? And then of course, I think Jason has, the paper has extension working on this, right? But with differential information provision, then I think that gives a little bit more reason to say that I want to price discriminate across different exchanges, right? So, and then a few other things, considerations. If you think about with only 2 advertisers, and you can have competition either within exchange or across exchange, but not both. And I suppose you have multiple connected advertisers. Then on the private exchange, I have multiple connected advertisers. So maybe the competition between them is already enough, right? So in this case, the dampened competition effect found in this paper itself is dampened because the competition between the collected ones is going to dominate, okay? So this gives actually immediate implication that private exchange has different implications for thick versus thin markets, okay? And the second one I'm actually quite interested is if you look a little bit beyond fraud, right? So in the paper, the publisher is organizing in the way exchange by itself. And I'm curious, why wouldn't have the platforms operate a private exchange as well? So the platforms would operate a private exchange and open exchange. So kind of like exchange within the exchange, okay? So I thought this may be the potential new line of research. Maybe look at the cooperative games, who is gonna team up with whom, with side transfers and so on. And then another thing I'm thinking about is from the fraudster's perspective, right? So there's extension looking at how the OX would have incentivized fraud. But you could also look at how the fraudster's incentive to actually commit fraud, right? Because now there are fewer people on the OX. So less scam, so possibly less fraud. But then on the other hand, if you think about advertiser heterogeneity, maybe the remaining advertisers on the open exchange are less sophisticated. And then it gives you more incentive for fraud, right? And I also want to tie this to kind of like unraveling my impression from reading Jason's notes, presentation slides that was not in the paper earlier, right? And it seems like the private exchange is taking increasing share over time and of course of open exchanges. I was wondering whether maybe the current model already gives you insights on why the PX is taking over OX, right? But if not, I would suggest to think a little bit in that direction. And then one more one is repeated interactions, but this is obvious. In the static game, you don't care less about fraud, right? Unless fraud hurts your profit today, but in a repeated game, the fraud hurts your profit in the future. So overall, I really enjoyed reading this paper, learned a lot, and I think it's an important contribution to a timely topic. Thanks.
Thank you, Chihong. That's very helpful. We should talk more offline about your discussion. Thanks.
Everybody, this is Kinshuk Jareth here. I believe there would be an organizer or a representative.
I can check. It's Solar. You can start, I guess.
Sorry, I couldn't hear you. It was very soft.
Can you hear me now?
Very lightly, but yeah, very soft.
I guess you can start.
Okay, good. All right, well, good afternoon, everybody. So, we have people presenting from the West Coast and now people presenting from the East Coast. And in the presentation in the middle, there was one from each side. So we're covering all time zones. So very nice to be here. Thank you to the organizers for admitting this paper to the conference. And let me share my screen, then I can start presenting. So is everybody able to see it? And you can hear me properly?
Yeah, it's fine.
All right, great. Perfect. So my name is Kinshuk Jareth. I'm from Colombia, and I'm going to present some work today, which is with Gorkhan Bostanji, who's a professor at UBC Econ, and Pinar Yildirim, who's at Wharton. So before I start, I'll just say that I won't be able to monitor the chat, I think. So if you would like to ask a question, just go ahead, unmute yourself and ask a question. You can just make it like that, keep it informal. And so don't hesitate to do that whenever you have a question. All right, so let me get started. So this paper is titled Negative Advertising and Competitive Positioning. And this is about negative advertising. So let's get started with that. Okay, so let's talk about positioning and advertising, right? So positioning, obviously, positioning a product think of a horizontally differentiated market. Positioning is obviously a very important strategic decision, an important marketing strategic decision. And so that obviously depends sort of which types of customers you're targeting, what you're designing your product for. Now, advertising, which comes after positioning, is obviously also a key strategic decision that informs consumers about products. Now, you can say that you can have so many different aspects of advertising. One of the main things that we're looking at in this paper, they're going to be that firms can say good things about their own products, right? They can say my product is so good and this and that. Or firms can say something not so good about a competitor's product, right? That this is a problem with their product and so consumers really should not be buying this product because this is the case, right? So it's really reducing sort of the utility of the perceived utility of the competitor's product rather than increasing the perceived utility of my own product. And that's what we call negative advertising, which is a little bit different from comparative advertising. So negative advertising is, let's say, a subset of comparative advertising, and there's a huge literature on both. So let me give you some examples of negative advertising. I'm sure we can all think of some, but one example, for instance, is back in 1988. There was American Express, and it was faced with negative advertising from Visa and MasterCard. So Amex had launched a new card and a new product, right? And the Visa and MasterCard started attacking them that this card has limited merchant coverage. So this was actually launched at the time of the Winter Olympics in 1988. And there were ads saying things like, in these Olympics will honor effort and hard work, but they will not offer Amex. Right, so things like that. So just to tell people that Amex is not being accepted at the Olympics. So this was like so effective and so persistent around that time that Amex started downplaying its new product introduction. So that's from the 1988. Then there have been these spaghetti wars, so to say, right? So what kind of, all these companies sell spaghetti. So there were spaghetti wars and spaghetti sauce wars. in the 1990s and 2000s, where different companies were saying sort of negative things about each other, why the other product is not so good. We all know that negative advertising is very widely used in political competition, right? So there's product competition and political competition, and we'll discuss both. And there's also a study which basically traces negative advertising, like known instances of heavy negative advertising all the way back to 200, 300 years, right? So it's been always around. It's like a known phenomenon. But one could also say that, we don't really see as much as we could have. So I'll get to what I mean by that point. So here is one example from the 2016 election, which I just got from CNN, right? So these two political candidates are saying saying basically bad things about each other, and they're positioned quite differently. Okay, so what is the impact of negative advertising? It obviously hurts the target of the negative ad, right? So if somebody says negative about my product, well, it hurts my product. But the interesting part is that it can also hurt the company doing the negative ad itself, especially if the products are a little bit similar, right? If there's some commonalities between them. So here is a quote from the CEO of McDonald's, who was commenting on the burger wars, right? So there's spaghetti wars and burger wars, and these wars really refer to the idea of negative advertising at this time. So this quote says that, look, if you've got a good product, you should say something good about it, but you shouldn't be tearing down someone else, because it's just not good for our industry as a whole. We lose people. I say something bad about your burger, you say something bad about mine, and people are thinking burgers are bad to eat. So we both hurt. And so that's sort of not good for both companies, right? For the advertiser who's doing negative advertising, and for the target of the negative advertising. And so we say that, look, the impact, we can look at this impact, right? But there's a broader impact, which is that negative advertising, we should expect it to interact with other decisions. So here are some things to sort of explain that. One, there is evidence to show that industry leaders, when I say leaders, I mean leading companies, they cannot avoid negative advertising wars, even though it harms all parties. Then another one is that, look, so this second one, and I believe you all can see my cursor, that if you have aggressive and damaging reactions are expected, right, from negative advertising, then an entrant, suppose there's an entrant who's thinking of entering a market, right? But if they think that there are aggressive and damaging reactions I will have, the entrant might be frightened off, might change their decision, right? So they might not even enter, or they might not enter on a less ambitious scale. Basically, what they're saying is an entrant might enter differently. And that's really what we're going to be looking at today. Also, there's this idea that political candidates, right? So there's a study that shows that, look, political candidates are less likely to use negative advertising when running against opponents who are ideologically similar to them, right? So what this also shows is that positioning, where you're positioned, that interacts with negative advertising, right? So there's sort of some evidence for all of these things. So going from there, we can say that, look, a rational entrant. So suppose there's an incumbent, there's a company already in the market, and there's an entrant. So the rational entrant would make its product design decisions, or should make, considering the advertising competition down the road. Like, once I enter and I position myself a certain way, this is the product design of my product, what will be the competition down the road, right? In advertising, like, how can I expect to be sort of negatively advertised against, and therefore negatively perceived by consumers, at least to some degree. And also, this kind of leads to an implication that, look, suppose we are not seeing negative advertising. It's not necessarily that's because firms don't want to do negative advertising. This may actually precisely be because firms are making competitive product design choices to prevent it, right? So you choose a product in such a way that the competitor is unable to do some negative advertising against you, right? That's the idea here. And that's really the idea underlying the paper. So this is to say that if negative advertising had not been permitted, people would have made, the companies, the entrants would have made their design choices differently, right? And I keep talking about incumbent and entrant. All of this very seamlessly applies to also, simultaneous entry. So we'll talk about that. Okay, so here I talk about had negative advertising not been permitted. So who will permit or not permit? Well, some policy, some regulator, right? So there is obviously a policy angle to negative advertising. So the FTC in the US, the FTC adopts basically somewhat of an encouraging position on negative advertising. So FTC says that, look, this is a source of important information to consumers, and it assists them in making rational purchase decisions. Okay, and this encourages product improvement and encourages innovation because people want to make a better product and so forth. In contrast, the European Union for a very long time, up until the late 1990s, had explicitly banned negative advertising. So the question arises, which one is correct? Like, what should a regulator do? Why would the European Union ban it? Or why would the FTC encourage it? I mean, FTC clearly saying there's an informative aspect here, right? But what are there hurtful aspects also of negative advertising? So we'll derive some welfare implications. So here are some research questions. So think of a horizontal product differentiation framework, right? The horizontal market, consumers are differentiated horizontally in their taste. And the question then is, when will firms do positive versus negative advertising? So I'm gonna keep track of the time. Okay, so that when will firms do positive advertising and when will they do negative advertising? Okay. In a horizontal product differentiation framework, when firms are sort of, let's say, exogenously, we locate them, right? We say you're located here and you're located here, what will happen? And then we can go one step higher. We'll say that how will this expected advertising competition after positioning influence positioning itself? And also once we see, so in equilibrium, there's some positioning, then what advertising will we see in equilibrium, right? So what will the equilibrium positioning be? And what will the equilibrium advertising be? And obviously that can vary under different conditions. And that's sort of the point of the paper, to understand all of that. Also, we will look at this question of welfare, that is it good for consumers or is it bad for consumers? And what are sort of the trade-offs here, of course. And then all of the first three I was talking about, it's more in the idea of a product differentiation framework, right? But what about political competition? Is political competition different? And why sort of do we see more negative advertising in politics than in products? I think we'll all agree that that is the case, right? So the question is, why do we see more negative advertising in politics and compared to products? So these are the broad motivating research questions. Okay. So let me give you the key idea of the paper, right? And the basic idea is that what we'll find is that the threat of negative advertising leads to, not always, but may lead to, I should say, an equilibrium of co-location with positive advertising. Right? So this is not to say that we'll never see negative advertising even with co-location, but this is to say that there is a pressure. The threat of negative advertising puts a pressure towards co-location with positive advertising. So if negative advertising is very hurtful, firms want to avoid it. And the way to avoid it is to co-locate. Why? Because if you co-locate, I mean, then your products are very similar. So you won't say too many negative things about a product that's very much like your own, because consumers will say, oh, if that product is bad, then your own product should also be bad, right? So that's sort of the spillover. There's a negative spillover. And when you co-locate, you essentially commit to not doing negative advertising, right? So that's sort of one of the main forces in the paper. But in political competition, this was for products, right? So what happens in political competition? We find that there is comparatively more, when I say comparatively, it's in comparison to product competition. So in political competition, there is more differentiation with negative advertising. So there's more differentiation in political competition and more negative advertising than in products. And the reason is that the objective function in politics is different. So in products, the objective function is that I want to maximize my profit. But in politics, the objective function is not so much to maximize profit, it's just to get a little bit more than the other person, than your competitor, and then you win the election, right? And so that actually plays a big role, because in this case, you don't really care about not many people voting, you know? So it's okay, people can be turned off and they might vote for nobody. They might just exit the election. The voters might just exit the election, so to say. But as long as that helps you, you know, that's okay, as long as you are getting more votes than your competitor, right? So product and political competition are quite different. So what we show basically is that is the same set of forces that are at play, but changing the objective function can have sort of a significant impact on sort of what we see as the equilibrium outcome. All right, so this is sort of the main idea. I can pause for a moment if people have questions, or I can go forward.
Yeah, so Kensher, one question I have here is that the way you just mentioned this contrast between regular products and political competition, is it fair to say that this is also similar to the comparison of covered market versus uncovered market? So in the political competition case, somebody has to be elected. Whereas in the product case, if I sell orange juice and if I keep attacking my rival's orange juice, consumers don't have to buy orange juice, they can buy milk.
Yeah, you can think of it. Yeah. So, I mean, we will see that the market might not be covered even in products, right? But that force, you would rather want people to buy your product. And so, yeah, that's
right.
Yeah.
Right. And the elastic demand versus inelastic demand.
Well, yeah, we don't have the total demand as elastic or inelastic. We use a hoteling framework. So we don't have the total demand as sort of elastic, but I mean, you can think of it as market coverage. If you think of that as elastic, then yeah. All right, great. So let me proceed. And there's a lot of literature, and I know, you know, there are lots of people here who worked on it. I'm just going to highlight the main points and highlight one paper. One is that there's sort of this competition with, there's a literature stream on competition with informative advertising, right? So lots of papers there, and some recent work, very nice work on consumer inferences from advertising, right? So that advertising is how is it working? Is that consumers infer something about the advertiser, something about the competitor, and so forth from the advertising action. Then there is competition with persuasive advertising. And as I said, I'll highlight one paper, and that paper is by the person who the conference is named after, Frank Bass, in 2005. And this is persuasive. We are more in an informative advertising, but it was very nice to see, you know, to see this paper as I was building my slides, and I was going through my own paper, of course, and I saw this, so that felt very nice. Then there is negative advertising with political competition, and there's some work on that. There's not a lot of work on that, but there is more and more coming up. So we obviously are related to that, right? And then there is work on product positioning, of course, which is, you know, all the way going back to hoteling. That's the main model we use. And there's some recent work also on that. So I know that there's a lot, that there must be people here who have worked on advertising, and I might not have written it here. This is by no means exhaustive. And you know, the paper has much more discussion of the related literature. But again, let me sort of highlight some of the important points also. The most important part is this point one here, that we are in a setting in where there is competition with informative advertising, right? That's the idea of the paper. And also we sort of have consumer inferences from advertising is going to be quite important in the paper. Now, having said that consumer inference from advertising are important in the paper, I will sort of contradict myself a little bit, because the way I want to present this work is to actually do it in two steps, okay? Which is that the first, I'll present a simplified model to communicate some main insights. So this is not the model in the paper, but this is almost the model in the paper, right? But here I will for the sake of the presentation and for easier exposition, I'm going to take some, some sort of leaps of faith or make some ad hoc assumptions, so to say, but it'll communicate the main insights. And then I'll step back and I'll say, okay, let's analyze one part of this model, which was not microfounded, which it should really be microfounded. And then we'll do that microfounding, build those microfoundations and plug some of these conceptual holes, which will bring the paper back to informative advertising and consumer inferences from advertising. And again, this paper by Shubhranshu and Ganesh here, this is a very relevant paper here. Okay, so again, this is the idea, is to communicate main insights, because I think that the paper itself, you have access to it. If you look at it, it's sort of conceptually not so complicated, but it's so unwieldy, and it's kind of, the math is a little bit cumbersome, that I thought that if I just start presenting that to an audience, I might lose them and the communication may not be so clean. And so that's why I'll follow this two-step strategy. All right. So, okay, here. So let me give you the simplified version of the model, okay? And I'll tell you where the simplification is. So we say that there's a hoteling line, not hoteling line, actually, there's a horizontal framework, right? And consumers are located at points L and R, and these are of equal mass, right? And these are a distance d apart, and this is obviously taste, not necessarily geographical distance, right? So it's not exactly a hoteling line, but it's with a hoteling line framework with two mass points, and one is L and one is R, okay? Now, so these are where consumers are located, and now there are two ex-ante identical firms, and first there is a location decision, and then there is an advertising decision for these firms. Now, I'll assume that there's an incumbent located at L, right? And an entrant has to decide their location as either L or R. So if you locate at L, there's co-location. If you locate at R, it's differentiation. And the utility of a consumer J, who's located, let's say, at XJ from firm I, and the firm is located at Chi I, and both XJ and Chi I are either L or R, right? So they can be the same, in which case this thing is 0, they can be different, in which case this thing is L. So the utility is some gamma, which is a sort of a baseline utility you get, minus a distaste, okay, plus this A sub I. So you will see already that there is no price here, okay? So we will assume firms to be price takers for the moment. Price is not a very important component of this whole theory, but we'll get back to that later. But that's not even the simplification I'm talking about. The simplification I'm talking about is this AI. So in this utility framework, the gamma has a distribution, right? And AI is an advertising effect. And here we're just assuming that AI is determined by the ad strategy of the two firms, the ad actions of the two firms. And it's just sort of a component that gets added to utility. Okay, now you might question that that's not, ads by themselves don't give utility. Ads should influence my beliefs about products. And then I have an expected utility about the product. So we will go there, but towards the later part of the talk, because I just want to communicate some main ideas. So that's what it says. We will revisit AI later. Okay, so let's look at the simplified AI, right? So ads are costless. We are assuming that, and can be positive for yourself or negative for competitor, right? So because they're costless, you'll do one of these. Now, a positive ad, we assume it has no effect, right? So again, oversimplifying a little bit. But a negative ad has an effect, right? So if I show a negative ad, then there's an effect of minus B on my competitor. We call it the direct effect on the competitor. But if there is co-location, if we are co-located, then there is also a spillover or a backlash on me, okay? And if we are not co-located, then the impact is 0 on me, right? So co-location, if there's negative ads and we are co-located, then I can hurt my competitor, but I might also hurt myself. While if we are not co-located and I do a negative ad, then I'll hurt my competitor, but I won't hurt myself. All right. So what are the advertising possibilities? Under co-location, right, what happens is if both do positive, so it's not what happens, but if both do positive, then there is no effect on anything. If I does positive and B does negative, then I has no effect on anything, right? I's ads is 0, but K's ads have some negative effect, which is minus B on I and minus beta on itself, because there's co-location. So this is obviously the flip of that. And here these effects exist in both because both are doing negative, right? So this is under co-location. What about differentiation? If they're not co-located but located apart, then positive ads have no effect, but negative ads have minus B, and this is just B0, not minus 0, but negative ads have if K runs a negative ad, then there's a effect of minus B on I and no effect on myself because we are not co-located, and also I did a positive ad, and so the positive ad has no effect on anything. And both can do negative ad, in which case it's minus B and minus B, right? So you can already see from this that if we are co-located and we do negative ads, then there's a big problem because both of us are hurting a lot. But if we are differentiated and we do negative ads, well, there's less of a problem. Okay, so this just sort of keep that in mind. Now let's look at the timing. Timing is that firm I chooses location, then firm K chooses location, and we can really just collapse this. It makes no difference really whatsoever. Now firms simultaneously choose advertising after that, and consumers choose whether to buy and from whom. All right. So let's get to the results. So suppose negative advertising was not allowed, and we know that it was banned in the EU until the late 1990s. So in the absence of negative advertising, if firms were, what happens is that the entrant chooses to differentiate its position from the position of the incumbent, and they both do positive advertising. Okay, so if you cannot do negative advertising, you don't co-locate, you actually differentiate, you get your own little market, and you do positive advertising. That's simple enough to understand. What if negative advertising is allowed? And we know that the US FTC actually encourages it. So what if we are co-located? If we are co-located, so when the entrant has chosen to co-locate with the incumbent, there's a unique equilibrium where both advertisers follow negative advertising. And this equilibrium happens under these conditions, okay? And under all other parameter sets, under minimal differentiation between firms, there's an equilibrium where both firms utilize positive advertising. So what is this saying? It's saying that under minimal differentiation, negative advertising happens basically when the spillover effect is kind of small. You can see beta is lower than B here, and you would expect that, right? And also beta is also small here, as you can see, right? So if beta is small, negative advertising can happen. Otherwise, under co-location, there is positive advertising. Now, what about maximal differentiation? That when the entrant chooses to locate differently than the incumbent, both companies utilize negative advertising if this condition holds. So I'll discuss these conditions later also, but basically there can be negative advertising in this case, but in the opposite of that condition, only positive advertising holds. All right, so we can put all of that together into this equilibrium, this proposition which shows the equilibrium. What this shows is that if market heterogeneity is large enough, right, if the two firms are quite different, if the taste is broad enough, then in equilibrium, the entrant differentiates its product and both firms run positive advertising. Why? Because there's no, first of all, you do want to differentiate if possible, right? You get your own little market. And if the taste heterogeneity is pretty large, then the spillover is not so bad. Then the effect of a negative ad on your competitor does not really bring those consumers to you, right? So the negative ads are sort of toothless and you run positive ads. So, and just say nice things about yourself. Otherwise, if market heterogeneity is not too large, this is the more interesting case, then there is a lot of action in the spillover, right? So if the heterogeneity is not very large, then for large values of beta, for large spillover, the entrant will co-locate with the incumbent and both firms run positive advertising. Why does the entrant co-locate with the incumbent? Well, because if you did not co-locate and you located separately, you would do negative advertising. And because the spillover is large, this negative advertising would also hurt you, okay? Now, if the spillover is small, then you can actually differentiate, right? And both firms run negative advertising in this case. Why? Because you differentiate, you run negative advertising on the other person, right? You get some of those customers, but actually the spillover is smaller, so the spillover doesn't affect you, right? But even in this equilibrium, these are actually prisoner's dilemma type of equilibria. And for intermediate values of beta, for intermediate values of spillover, both of these equilibria hold. So I think I said a lot of things. Let me put that in a different pictorial manner. Just want to keep track of the time. So in a pictorial manner, so what does this table show? This is the entrant. So this column is saying whether you're co-located or differentiated, right? And this is saying positive is the equilibrium action and negative. So these are all the different conditions under which equilibria happen, all right? So first you can see that under co-location, there is no negative advertising. Under co-location, we are only finding positive equilibria. Second, when the taste heterogeneity is large, so remember that D was the distance and B was the negative effect of the ad. So when the taste heterogeneity is large, then you differentiate and do positive advertising. Why? Because B is not so bad that people will actually switch. Okay, so there's no point doing negative advertising, so you just do positive. The more interesting case happens when taste heterogeneity is small. So this is the off diagonals are the diagonals are like that. So this shows that when the taste heterogeneity is small, so D is small, but the spillover is large, it's pretty large in this case. Then what you do is you co-locate and do positive ads, right? Because if you did not co-locate, if you differentiated, you would do negative ads and the spillover would also hurt. So, I mean, there's just no sense doing that, right? So B is large and beta is large. This condition says that if taste heterogeneity is small, right? So D is small, but B is larger than D. And also beta is small. So if taste heterogeneity is small and spillover is small, and this also says spillover is small, then you differentiate and do negative advertising. Okay. So basically, again, what's happening here is that if the taste heterogeneity is small and the spillover is not too bad, you do differentiate and do negative advertising, right? But if the spillover is large, then you co-locate and do positive advertising. And these two conditions are actually the same condition. And here it says that if the taste heterogeneity is small, but the spillover is medium, then you can have both of these conditions. So really what has been shown here is that, look, there is no negative advertising under co-location. That's not an equilibrium, and co-location is leading to positive advertising, and co-location is a way to commit to avoid negative advertising when negative advertising is very hurtful. Okay, so I kind of said this already, but I'll just show that we can also use these results to determine some comparative statics, right? So suppose consumer taste heterogeneity is small enough, then the action is in the spillover from negative ads, okay, like we just discussed. And so what is the impact of the spillover or the backlash? So if consumer taste heterogeneity is small enough, that is that negative advertising has some impact, then small spillover leads to differentiation with negative advertising. But large spillover effect leads to co-location with positive advertising. Okay, so as the spillover becomes larger and you don't want to do an ad which kind of hurts yourself, so you also co-locate and you do positive advertising. Now we can get to results on consumer surplus and firm profit. And so consumer surplus and firm profit are actually higher when firms locate apart and do positive advertising. Okay, because they're located apart, so there's every segment is being served and there's positive advertising, which is also good. However, when the spillover was large, what we saw that the threat of negative advertising with large spillover led to firms to co-locate, right? And this hurt consumer surplus. So what's really happening is that in equilibrium, you do not even see negative ads, right? But their mere possibility that they can be done may lead to surplus destruction because of co-location. So that questions whether the encouragement of the negative advertising by FTC is always such a good idea, right? Because what's happening is that negative ads are leading to firms to co-locate and not serve the market properly, because they're worried that if they do not co-locate, there'll be a lot of negative advertising. So they co-locate and they commit to not doing negative ads. So that's sort of an important implication of this. So I have about 10 minutes. So let me discuss some extensions in that, and then I'll go back to my sort of micro-founded model. So one is, these extensions are more like robustness checks, right? So one is simultaneous entry. So in simultaneous entry, really nothing changes except that for every co-location equilibrium in the sequential entry game, there are two equilibria in the simultaneous entry game, one for each location. So that's all that changes, nothing else. So another one is endogenous pricing. So in the main model, firms are price takers, and this helps with co-location because, if they're price takers with co-location, you don't compete away price. And that's really the problem of endogenous pricing. But all results go through as long as price competition under co-location is not too intense. So how do we do that? To achieve this, we sort of follow the framework from Diamond, the famous Diamond paradox and a framework. We follow the framework for Diamond, which is also used by Dimitri in one of his papers. So we say that, look, there's a search cost for pricing, for finding out price. And if that is the case, then this softens competition, right? So indeed, prices will be lower under co-location than under differentiation, but they will still be high enough under co-location that firms want to co-locate and do positive advertising for large spillover. So results basically don't change. They're only in a tighter parameter space. Then we come to political competition. So again, what is the motivation to study political competition? The motivation is that our model of product competition is predicting co-location with positive advertising. But in politics, we very often see polarization with negative advertising, right? So we want to sort of generate that. So we say that, okay, what is different in political competition? The difference mainly is not in the forces, but in the objective function. And the objective function is not to maximize profit, but just to win by plurality. And so we adjust the model for this, just the objective function, and that's it. Everything else is the same. And the insight then is that in political competition, candidates don't really care about a reduction in the total number of votes polled, as long as they have more votes than the competitor. And so negative advertising, because of which market coverage can reduce, negative advertising is more acceptable. And the result here, therefore, is that we find that in political competition, indeed, there is more differentiation along with negative advertising compared to product competition, right? So our same model, just changing the objective function, indeed allows us to get this result that in politics, we will see more differentiation and accompanied with negative advertising than in product competition, which I think is reality. Okay, so now this basically, I could finish the paper here, but I want to go back and sort of plug in this conceptual loophole and but just provide a micro-founded consumer model. Okay, so let's think of this advertising effect AI, right? So we said that, look, there is this utility and AI is determined by action, by advertising actions. But you could question that, look, advertising does not change my consumption utility. So this is not a very good model, right? What advertising should do is advertising should impact the utility through inferences on the value of the product. So we do that, right? This leads to a more palatable model while producing basically the identical insight. So think of whatever I've said, just as you think of it as everything holds, except that we will work on this AI and it'll still work in the same way, but we will microfound it. So what we say is that AI is now will be interpreted as the value component of firm I's product that can only be learned from advertising actions of the firm, right? So advertising is not giving utility. Advertising is changing my inferences, my inferences about the product, so that I know what my expectations of what utility I get from the product are different, right? So that's the whole point of informative advertising. And again, this is the paper by Shubhranshu and Ganesh, which has a similar approach, right? So there's sort of these Bayesian consumers who are making Bayesian inferences. All right, nothing else in the model changes pretty much. So let's look at what we do with this AI. So the model now suddenly gets pretty complicated, right? I mean, it's still nice, but it's kind of a lot of components here. So we say that each product now has, so the line is—
Can you check?
Yeah.
You have like 5 more minutes.
Yeah, thanks. So we say that each product has one horizontal attribute, which is location, right? And two potential vertical attributes, one of which is positive and one of which is negative. So a product is defined as this triplet, right? Location, whether there's a positive attribute and whether there's a negative attribute. And the positive attribute can be there with probability sigma and sigma pi. And if it is there, it gives utility plus pi, okay? And if it's not there, there's nothing. And there's a negative attribute, which is there, it's probability sigma beta. And if it's there, it gives a utility of minus beta, otherwise it gives nothing. So the firm decides the location. And after that, nature draws these vertical attributes, which firms observe, but consumers don't observe. Okay, so firms observe them, but consumers can only infer them from the ads. Now, horizontal location influences the realization of vertical attributes. So if the products are co-located, then the realizations of their positive and negative attributes will be correlated because they are similar products. And if the firms are not co-located, they're differentiated, then there is no correlation between the realizations of their attributes. Okay, so this will lead to the spillover. So, so consumers know the horizontal location and they know the structure for vertical attributes, how they are drawn. And the firm can do one of the following, and advertising must be truthful. That firms can do positive advertising. That is, they can tell consumers about your positive attribute if you have it. So, right, so you tell consumers about your own positive attribute if you have it. They can do negative advertising. That is, they tell consumers about competitors' negative attribute if the competitor has it. Or they can do no advertising at all. And then they tell consumers nothing, right? In this case, they tell consumers nothing. But the point is that each of these actions will now lead to some inferences because consumers know this structure. Okay. So now, again, the timeline, just to clarify, is that the entrant chooses its product position, the nature draws and firms observe, and the attributes theta are the vertical attributes. Then the firms choose their advertising strategy, and then consumers update their inferences and they make their beliefs, right? And they decide whether to buy something and which one to buy. Okay, so this is really the last main slide, or second last. Three effects of advertising appear. There are three effects of advertising on consumer inference. I thought this was a build, but it is not. So let's look at this one. The first is the direct effect, right? So the firm tells the own positive or competitor negative attribute, and then consumers know it exists and advertise, right? So you can just tell, look, I I have a positive attribute, and the consumers have to believe it because advertising is truthful. Or they can say competitor has a negative attribute if it indeed exists. And so consumers know that this product has a positive attribute or a negative attribute. The second is the inference effect, which is that what consumers infer about non-reported vertical attributes from advertising action. For example, if a firm does no advertising, then consumers say that this firm must not have the positive attribute, and also the competitor must not have the negative attribute. Otherwise, this firm must have done one of these. Okay. And under certain conditions, if a firm does positive advertising for its own product, then consumers can infer that under these conditions, the competitor must not have a negative attribute. Otherwise, this firm would have been benefited more by doing that. The third is the spillover effect, which happens only under correlation. And let me just walk you through an example. So suppose that firms are co-located and firm 1 does negative advertising and firm 2 does positive advertising. Okay. So then consumers learn about P2. They know that there's a positive attribute for product 2 because firm 2 has done positive advertising for itself. They also know that product 2 has a negative attribute because firm 1 has done the negative advertising for this product. And they also know that under certain conditions, product 1 does not have the positive attribute, okay, because otherwise the firm did not talk about it, right? But none of these actions tell anything about N1. N1 is whether the firm 1 has a negative attribute. However, because of co-location, consumer can infer something about N1. Consumer knows that N1 and N2 are co-located and they're correlated and therefore co-located. And therefore the consumer infers that if N2 exists, then N1 must also exist with a certain probability, which is more than the prior probability, which was just sigma p. Okay, so this is the spillover effect. So really the effects are the same. You can see direct and spillover, and there's this inference effect, which you have to account for. But earlier I was only talking about direct and spillover, and I was just sort of ad hoc assuming them, but now we are just deriving them. So we do all of this for all possible advertising combinations and this and that, and we use this in the expected utility of the product, right? So advertising actions update this, and so therefore there's an expected AI, then consumers make choices. And so these are the insights from the micro-founded model, and this is also my last slide. This is the summary of the whole paper really, and these insights are basically identical to the other model I'd shown you. So what does this model produce? It tells us, and again, these are the summary, this is a summary of the results. One, that there is more, so what we say at the end of the paper is that there is more negative advertising under differentiation than under co-location. Okay, because under co-location, consumers will say, oh, you're saying something bad about that product. You must also have something bad because the products are so similar. Second, there is incentive to co-locate to commit to not doing negative advertising. And so the policy implication that comes out of here is that negative advertising provides more information, which is good for consumers, okay? But it may lead to less differentiation. The possibility of negative advertising may lead to less differentiation, which is bad for consumers. So in equilibrium, you might see that there is co-location with positive advertising. So negative advertising was not even used. So there was no informational effect. But because it could have been done, firms co-located, and that's obviously not good because they're not, the market is not served as well. And also, you can say that there was this the results with spillover. The same results appear here. This is say that if there is low prior uncertainty on realization of negative vertical attributes, that leads to more co-location. This is similar to saying that if spillover is large, then leads to correlation, because if there's low uncertainty that there's a negative attribute or not, that means spillover is more likely to exist. It's really, the model is totally almost a one-to-one. So then the third is that price competition reduces the incentive to co-locate, but as long as this doesn't drive the prices to zero, these results will hold. And finally, we have the result that product and politics are different. The forces are the same, the outcomes are different because the objective functions are different. So in political competition, we will see more differentiation with negative advertising accompanying that differentiation. So those are the insights of the paper, and thank you very much, and look forward to the discussion.
Okay, can you see my screen?
Yes, okay.
Right, so my name is Ucharjin. I'm from University of Florida. And let me start by thanking the organizers for putting me as a discussant for this paper. I had a lot of fun reading this paper. And this paper is very detailed and very kindly explaining everything. So, I mean, I enjoyed the process a lot. But the only thing is that, I mean, it is very long, so I wish I had seen the simplified version that Kinshi just presented, I mean, earlier. But I mean, anyway, so but the paper is great, and I had a lot of fun. So in my discussion, I'm just going to go over some of the big insights of the paper. So the paper is about negative advertising. So we have seen a lot of examples of the negative advertising out there. So one of the examples is here, I mean, which is the advertisement by Samsung back in 2014. Probably you need to know the context and to understand what they're trying to say here. So back in 2014, when iPhone 6 was introduced into the market, people quickly found out that the iPhone has some problem with its frame. So that even with a small pressure, I mean, the frame is going to be easily bent. So taking that, I mean, Samsung made an advertisement saying that bent to those who are worthy. So actually, it's making fun of Apple, of course, and then they, this type of advertisement is going to hurt the competitor Apple here, of course. So given that there are lots of, I mean, actual practices, I mean, where there are negative advertising, and also negative advertising is harmful. I mean, firms would think about the ways to avoid negative advertising. So one of the ways might be to change the product differentiation, product positioning. So that's where I guess, I mean, the authors have started, I mean, thinking. So in this paper, they were wondering whether negative they could avoid, I mean, the firms could avoid negative advertising by doing product positioning differently. So, and they formalized this idea by asking, what is the impact of the negative advertising on the product positioning? And also, they also look at, I mean, given that different countries have a different type of the regulations on negative advertising, they were asking, what is the welfare impact of the regulation on negative advertising? So these are the big questions of the paper, as far as I understand. And then these questions are answered by the simple model. Well, I mean, their model is not actually simple, but I mean, here are some of the key components of the model. So in the model, there are, I mean, products with 3 attributes: one horizontal, 2 vertical, and 1 positive and 1 negative attribute. And all of those attributes are binary in the sense that you have only 2 choices. So for the product positioning, which is a horizontal attribute, you can either position your product on the left side of the market or right side of the market. And of course, I mean, on both sides of the market, there are consumers of mass 1. So essentially, you're choosing what type of consumers you're going to serve. And then for the vertical attributes, your product could have either have positive attribute or not. And your product also could have either negative attribute or not. So in that sense, I mean, these are binary choices, binary characteristics. And one thing that is important here is that the horizontal attribute can be observed from the product design, but vertical attributes are not observed, but it can be inferred from the advertisements. So that's why firms are engaged in the positive versus negative advertising in this model. So there is, the authors consider 2 firms: incumbent, who is sitting on the left side of the market. Then for the entrant, I mean, there are only 2 choices for the positioning: either sitting in the same side with the incumbent, or sitting on the other side, than the incumbent. If entrant position itself in the same side, then because their products are similar, their vertical attributes are correlated. So their correlation across the correlation of the vertical attributes across the products is going to be positive. But if the entrant is positioned far away, then the correlation is going to be zero. And this is actually the key assumption of the model. So, and because there are some uncertainty on the vertical attributes, the firms do advertising, and there are three choices. First, talking something good about their own product. Second, talking about some negative aspect of the competitor's product. And third, no advertising. So from these three advertising choices, actually firms are trying to influence the consumer's inference on the vertical attributes. And this type of advertising could have either, the direct effect and also indirect effect, which are the inference, consumer's inference about the unadvertised product, unadvertised attribute, or some of the inference from the spillover effect when they are co-located. So based on that, the consumers will make the purchase decision. They could either buy one of those products or buy nothing based on the utility. But utility is a standard utility, so I'm not going to talk about that. With that setup, the biggest message of the paper is that firms may choose undifferentiated positioning in order to avoid competitors' negative advertising. And the insight is simple. If you understand the setting, right? If the entrant, if the two firms are collocating, then because of the correlation of the virtual traits across two products, if the incumbent or if one of the firms do the negative advertising, then there will be spillover effect, which will hurt the demand of itself. So when they are co-located, firms will have an incentive to avoid negative advertising more than when they are located apart from each other. But that is really what induces the undifferentiated product positioning. So that is one of the biggest message of the paper. And this actually has a welfare implication. So typically, negative advertising provides more information to the consumers, especially the negative information about the competitor's product, so that consumers can make more informed choices, which is a good thing to the consumers. But at the same time, negative advertising could lead to reduced product differentiation. So because of the reduced product differentiation, some of the consumers in the market would not be able to buy the product that they really want to buy, just their ideal product. So that hurts the consumers. So in the end, the overall welfare impact could be negative. And this is negative, especially when the first positive effect is relatively small. And that happens when consumers have sufficient prior information about the negative attributes. So that's another big message of the paper. And then they went on to examine the political competition context. And they find that the negative advertising is weakly more likely in political competition than in product competition. And as Kenshuk already explained very well, the reason why this is happening is because there are different objectives between product competition and political competition. The product competition, firms are trying to maximize the number of sales, whereas in the political competition, you can just win relatively more number of votes than your competitor. So whenever there is a negative advertising, there might be some shrinkage of the overall market demand because you are reducing the utility of some of the consumers. That actually hurts in the product competition. That could actually hurt the firms who are doing negative advertising in the product market competition. But this is not so in the political competition, because all they care about is the relative number of people that they get. So even if they lose some of the votes, As long as they can decrease the number of votes for the competitor, then they will be fine. So there will be more occasions where they adopt negative advertising. So that is the equation for the third result that I think is good. So there's a lot to like about this paper. One thing is that we see a lot of examples of negative advertising in reality, but we don't really have a lot of theory on this important topic. And the paper provides one theory on this. So this is clearly a contribution to the literature. But I especially like the paper because of its novel perspective on the relationship between the negative advertising and the product design. And this is something that if you understand the setting, then it's easy to understand, but this is not something that is easy to come up with. So in that sense, I think that the paper has a sufficient substantive contribution. And also the paper has a clear policy implications. So I like this paper a lot. But there are some comments that I would like to say next. So one of the things, one of the critical assumptions of the model for the main result is that the horizontal attribute similarity implies cross-product correlation of the vertical attributes. But if you really think about it, this may not be applicable to every horizontal attribute. So for example, think about a color of a car. The color of the car may not have a lot to do with the performance of a car. So having, let's say, white car instead of blue car may not say much about the performance of a car. But in fact, the type of a car, like SUV, trucks, or sedan, could have some implication to the performance of a car. So in that sense, so that makes me wonder whether this is really the horizontal attribute that actually leads to the information spillover across the product, or is there any true characterization of the condition for this information spillover? So I thought about it, but my answer is not complete yet. But so far, what I think is that it is actually the attribute that can define some subcategories of the product, like in the case of the car types. And so if the attribute can define some subcategories, then it would lead to some information spillover. So my point here is that the authors may want to, to think about what is the true characterization of the condition for these things to happen. Another point about another point is about the advertising cost. So currently in the paper, advertising is costless, and this is good because it helps us to understand better the forces of the model clearly. But what if the advertising is really costly and the advertisers care about it? Of course, the firms would advertise less, but there might be some strategic effect as well. So on the core, for example, on the co-location, advertisers may want to free ride on the competitors' positive advertising because of the spillover effect. If that is the case, then not only the negative advertising, but also positive advertising could lead to co-location decision. And also, this may weaken the negative welfare impact of the negative advertising, that is through the reduced product differentiation, because not only the negative advertising, but also positive advertising could lead to reduced product differentiation. But this is something, this is not very critical, but still, I would like, this might be some interesting extension model. Lastly, probably I don't need to say this because, the Kinshuk already presented a simplified model. But when I was reading the paper, I feel good because, the analysis was very thorough and detailed. It almost feels like a tutorial for the doctoral students. In that sense, I like the paper, but at the same time, I was wondering whether the same insight can be delivered in a simplified model, and which Kinshuk already did. So I just suggest a few ways of simplifying the current, micro-founded model. but I don't need, given the time and also, I mean, given that Kinshuk already talked about the simplified model, I don't need to discuss that. But I mean, probably Kinshuk can take a look at it, and then, I mean, if you think this is helpful, then you can also think about it. So this is pretty much that I have about the paper. So I really enjoyed the paper, and I think this is a great paper that has a lot of contribution. I again thank you for, using me as a discussant, and thank you for your attention.
Thank you very much, Buchel. Yeah, thank you.
Thank you.
Really discussed the paper, the most important aspects of the paper, and also the additional sort of the thoughts that you have. They're very, very useful, especially the one on positive advertising, and also sort of the positive advertising can also lead to co-location, and also the other one, the first one, that's also very important, that how to define that under which horizontal attributes can there be sort of co-location versus, I think the quick answer to that is that if an attribute value is such that it can invite a negative ad, then that is also that's something that can lead to co-location. Right. So I mean, nobody will say, oh, that Audi will never say BMW is making a red car. That's so bad, right? But they can say that, look, the BMW cars only are rear wheel drive and that's not good, or something like that. So, right. So if something can be criticized, then that can lead to the pressure towards co-location. Maybe that is one way to think of it.
Yeah, I agree. And for the positive advertising thing, I mean, I understand that the paper is totally about the negative advertising, but I thought probably it could be an extension or some other paper, I guess.
Yeah. I mean, I think we can sort of subsume that by changing the sigma beta. We can just, let's say we make that 0, and then there'll never be a negative attribute, right? There'll be only positive attributes, and then see what the results are.
Right. Yeah, that's one way.
There will be a subset, some parameter space where there will be co-location because of what you're saying, because of the free riding. So yeah, I think that's an important qualification to the result.
Yeah. I believe there will be a parameter space that.
Yeah, I got to run too, guys. It's good. Wuchel, thanks for doing this. Kinshuk, good to see you.
Yes, good to see you.
I have to run to teach. Take care.
Okay.
Thank you.
Yeah, thanks again, Wuchel, and thank you everybody else.
Thank you, everyone.
Thanks.
Thanks, Kinshuk.